Welcome to the Sleepy Scientist, a calm corner of the universe where you can drift through ideas while you drift towards sleep. Tonight, we're unraveling one of the most breathtaking secrets of the cosmos, the vast, invisible skeleton that holds galaxies, clusters, and even entire superclusters in place. The cosmic web, an immense and delicate structure stretched across billions of light years, shaping the universe in ways we're only beginning to understand. Before we begin, I'd love to know where you're listening from. Are you tucked under a blanket somewhere in the northern hemisphere, perhaps with the sound of rain outside your window? Or maybe you're far to the south, where the constellations take on unfamiliar shapes. Share your corner of the world in the comments. It's always fascinating to see just how far these invisible threads of curiosity connect us. And one more thing. If you'd like to explore the world a little closer to home, please check out our new channel, The Sleepy Geographer. You'll find the link waiting in the video description. If this kind of gentle science helps you relax, I'd be truly grateful if you gave the video a like and subscribed for more. And to those who have already subscribed, thank you. Your support is the quiet gravity that holds this little channel together. Now I should give a small warning. My hope is that this video soothes you towards sleep, but the universe is a tricky storyteller. The cosmic web is so beautiful, so strange, and so utterly vast that it might just keep you awake with wonder. If that happens, well, at least you'll be a little wiser when morning comes. So settle in, let your shoulders sink, and allow your breathing to slow. Close your eyes if you wish, and imagine yourself suspended in the great dark, surrounded not by emptiness, but by faint and delicate threads stretching in every direction. Tonight we are following those threads, wandering across the hidden framework of the universe. And to begin, let me ask you this. If the universe is mostly empty space, why does it look so much like a web? From a distance, the universe appears scattered, as though galaxies were tossed like glitter across a dark canvas. But look closer, not with human eyes, but with the patient eyes of telescopes and surveys, and a hidden order begins to emerge. Galaxies are not scattered at random. They flow together, aligning along threads of invisible matter, clustering where the threads knot, and leaving behind vast, hollow voids in between. This quiet architecture is the cosmic web, and it is the scaffolding on which the entire universe is built. The story of the web begins in silence. In the earliest moments after the Big Bang, the universe was astonishingly smooth, the same in every direction, with only the tiniest hints of difference, ripples so slight they might have seemed meaningless. Yet from those subtle beginnings, gravity went to work, tugging gently, patiently, gathering matter into the faint outlines of structure. Over billions of years, those outlines sharpened into filaments, into clusters, into something so large that even light takes hundreds of millions of years to cross it. The cosmic web is not something you can see directly. It is like the skeleton inside the body of the cosmos, invisible but essential, shaping every contour and curve. Without it, galaxies would not know where to form, stars would not gather, and perhaps life itself would not have had a chance to exist. And yet, for most of human history, no one even suspected it was there. Only in recent decades, with the power of mapping, surveying, and simulating the cosmos, have astronomers begun to uncover this hidden design. But the web is more than science. It invites metaphor. It asks us to see the universe not as chaos, but as a tapestry, threads woven together across unimaginable distances. It reminds us that emptiness is never truly empty. Even in the vast void, there are shapes, patterns, and connections waiting to be revealed. In the chapters ahead, we will drift through this hidden structure together, from the smooth beginnings of the early cosmos, to the gravity that drew the first threads tight, to the maps and simulations that let us glimpse the unseen. We will visit the nodes where galaxies gather, peer into the great voids where almost nothing resides, and reflect on the strange poetry of a universe bound by threads. And as we move through the story, one question will follow us like a quiet echo. If the cosmic web shapes everything we see, what else might it be shaping that we have not yet learned to notice? The story of the cosmic web begins not with threads, but with stillness. Picture the universe in its first moments, immediately after the Big Bang. What surprises many people is that it was not the chaotic explosion the name suggests. Instead, it was a remarkably even and uniform soup of particles, light and energy, spread out across all of space. The cosmos was hot, dense and expanding quickly, but it was astonishingly smooth. If you could have floated there with a thermometer, it would have read almost exactly the same temperature no matter which direction you turned. This smoothness is one of the great marvels of physics. The early universe had only the tiniest of variations, small ripples in density so slight that they were just 1 part in 100,000. Imagine a perfectly flat sheet stretched across a frame. To the naked eye, it looks flawless. But if you could run your finger across it with incredible sensitivity, you might notice faint wrinkles, almost imperceptible bumps. Those tiny imperfections are what seeded everything that exists today. Every star, every planet, every galaxy. Without them, the universe might still be a bland soup of particles, never giving rise to structure, beauty, or even life. Our strongest evidence for this smoothness comes from the faint glow that still surrounds us, known as the cosmic microwave background radiation. Discovered accidentally in the 1960s by 2 radio astronomers, Arne Penzias and Robert Wilson, it is the cooled remnant of the universe's earliest light. Back then, the cosmos was about 380,000 years old, practically a newborn by cosmic standards. At that age, the universe had expanded and cooled enough for the first atoms to form, allowing light to travel freely. That light has been journeying ever since, stretched into microwaves as the universe continued to expand. Until today, it appears as a uniform background filling the sky. When scientists mapped this radiation with exquisite precision, they found something extraordinary. It was not perfectly uniform after all. There were tiny variations, slight patches a bit warmer or cooler than their surroundings. These temperature differences reveal the density ripples from the early universe, the same faint wrinkles in the cosmic sheet that gravity would later tug into threads. They are the fingerprints of the cosmos at its infancy. If you want to know what the universe looked like before stars, before galaxies, before anything that could even be called structure, this is it. A glowing fog with subtle spots, like freckles on the face of eternity. One might wonder why the universe was so smooth to begin with. After all, when things explode, they usually scatter unevenly. The answer lies in the physics of inflation, a rapid expansion thought to have occurred in the tiniest fraction of a second after the Big Bang. Inflation stretched space itself at an unimaginable rate, ironing out irregularities like a baker rolling dough until it is smooth and flat. Yet, at the same time, quantum fluctuations, the jitter of energy at the smaller scales, were magnified into the faint ripples we see today. In other words, the universe was both smoothed and wrinkled in that instant. Smoothed on large scales, wrinkled on small ones, and those small wrinkles would one day become the scaffolding of cosmic architecture. For the first few 100 million years, though, the universe remained in its calm infancy. There were no stars twinkling in the darkness, no galaxies whirling in elegant spirals. The cosmos was filled with a thin, even fog of hydrogen and helium gas. If you could drift through it, you would see nothing but a dim red glow slowly fading as the universe expanded further and cooled. It was a quiet, almost featureless era, sometimes called the Cosmic Dark Ages. The only drama taking place was invisible, the faint tug of gravity gently coaxing slightly denser regions to grow denser still, while emptier regions grew emptier. The stage was being set, but the curtain had not yet risen. It is worth pausing to appreciate just how delicate this balance was. If the early universe had been perfectly smooth, with no variations at all, then gravity would have had nothing to work with. No seeds for structure, no filaments, no clusters, only an endless spread of featureless gas. On the other hand, if the early fluctuations had been too large, the universe would have collapsed into black holes almost immediately, snuffing out the chance for galaxies and stars to emerge. Life, as fragile as it is, depends on that narrow balance between smoothness and imperfection. The cosmos walked a tightrope, and we are here because it did not stumble. Scientists sometimes describe the cosmic microwave background as a baby picture of the universe, and like a baby photo, it is both ordinary and astonishing. Ordinary, because at first glance it is just a mottled pattern of faint colours. Astonishing, because hidden in that pattern is the blueprint of everything that followed. Every cluster of galaxies, every cosmic void, every structure we marvel at today began as a tiny blotch in that ancient glow. In a sense, the early universe was whispering its future in code, and only now do we have the tools to listen. What is striking is how serene this beginning truly was. For all the talk of the Big Bang as a fiery explosion, what it gave rise to after those first fractions of a second was a calm, almost featureless expanse. A universe that looked the same in every direction, patiently waiting for gravity to begin its long, slow dance. The cosmic web was already written into those first ripples, but invisible, like ink on parchment waiting to be revealed. And so the smooth beginning is less like a bang and more like a breath, a gentle exhale into the void, filling space with light and matter in equal measure, balanced almost perfectly. Out of that calm, gravity would one day pull threads, weave filaments, and carve the great structures we now call the cosmic web. But in those first quiet moments, the universe was simply smooth, glowing softly, and waiting for time to work its wonders. In the vast calm of the early universe, there was a secret restlessness hiding beneath the smoothness. Space itself was not entirely serene. On scales far smaller than atoms, reality is never perfectly still. It quivers. This jitter is known as quantum fluctuation, the restless hum of existence at the tiniest possible level. Even in a perfect vacuum, where there seems to be nothing at all, energy flickers in and out, particles pop up and vanish, and uncertainty rules. It is this microscopic uncertainty, magnified by the early expansion of the cosmos, that seeded the ripples in nothing, the faint wrinkles that would eventually grow into galaxies, clusters, and the cosmic web. To understand this, imagine a perfectly calm pond. At first it looks still, but look closer and you'll see that the surface is never truly flat. Tiny disturbances ripple across it, barely visible, stirred by the faintest breeze or the motion of a hidden fish below. Now imagine that pond suddenly expanding faster than light, stretching those tiny ripples outward in an instant. What began as minuscule wiggles becomes large, noticeable waves spread across the whole surface. That is essentially what happened in the early universe. Inflation took the quantum jitters of space and blew them up to cosmic size, imprinting them on the fabric of reality itself. These fluctuations created slight differences in density, regions where matter was just a little more concentrated than average, and regions where it was a little less. The difference was extraordinarily small, barely 1 part in 100,000. Yet that tiny contrast made all the difference. Over billions of years, gravity amplified those slight excesses of matter, pulling more and more material toward them, while emptier regions were drained further still. From such fragile beginnings, the skeleton of the cosmos began to take shape. It is almost humorous in a cosmic sense to think that everything we see around us owes its existence to what is essentially quantum fuzziness. The Milky Way, with its hundreds of billions of stars, the sun shining steadily for billions of years, the Earth spinning with its mountains, oceans, and living creatures, all of it can be traced back to tiny quantum whispers in the very first moments of time. The universe is not only stranger than it looks, it is stranger than it should even be allowed to be. The evidence for these primordial ripples lies once again in the cosmic microwave background radiation. High-resolution maps like those from the Planck satellite reveal patterns of warmer and cooler spots scattered across the sky. These are the fingerprints of the quantum fluctuations stretched by inflation. The warmer regions represent slightly denser patches of matter, and the cooler regions represent slightly thinner ones. If you rotate such a map around, you can almost imagine it as a cosmic weather forecast, showing highs and lows across the young universe. Except instead of predicting storms and sunshine, it is predicting where galaxies and voids will eventually appear. One of the most fascinating aspects of these fluctuations is how precisely balanced they are. If the variations had been even a little larger, the early universe would have been far more chaotic. Matter would have clumped so violently that black holes might have dominated everything. If the variations had been smaller, on the other hand, gravity would never have had enough of a head start. Galaxies and stars might never have formed at all, leaving the cosmos as a cold, thin fog. It is as though the universe was tuned with exquisite precision, creating the perfect amount of imperfection. Just enough wiggle in the smoothness to make complexity possible. Quantum fluctuations are not like ripples on a pond in every respect. Unlike familiar ripples, which are caused by something external, quantum ripples are intrinsic. They arise from the uncertainty principle, the rule that says certain properties like position and momentum can never both be known with perfect accuracy. This uncertainty ensures that even empty space cannot remain empty. It is restless at its core, with fields fluctuating at all times. When the universe was smaller than a proton, these fluctuations occurred constantly, bubbling and vanishing. Inflation then froze them in place, stretching them across space so that they became part of the universe's blueprint. Another way to picture this is to imagine baking bread. The dough begins smooth, but inside it there are tiny air bubbles forming at random. If you let the dough sit, those bubbles expand, and when you bake it, they become the structure of the loaf. The cosmic web is rather like that loaf of bread on a vastly larger scale, its bubbles and pockets representing voids, and its denser parts forming filaments. What began as microscopic randomness eventually defined the large-scale texture of the universe. It is tempting to think of these fluctuations as insignificant, but they are anything but. They are why the night sky is speckled with stars instead of being blank. They are why matter gathered into galaxies, why planets formed around stars, and why life eventually emerged. Without the restless uncertainty of quantum mechanics, the universe might have remained forever smooth and lifeless. In that sense, every starry sky is a monument to randomness, a reminder that order and beauty can grow from the smallest seeds of chaos. Scientists can even measure how those early ripples influence the arrangement of galaxies today. Surveys that map the three-dimensional positions of millions of galaxies reveal the large-scale structures that arose from the initial density differences. The scale of the ripples matches predictions from quantum fluctuations remarkably well. What began as tiny bumps in an invisible field has been confirmed across billions of light years as the guiding pattern of the cosmos. There is also something deeply poetic about this origin. The grandest structures we know, walls of galaxies stretching hundreds of millions of light years, were born from the tiniest possible uncertainties. The largest came from the smallest. The quiet shiver of quantum fields became the sprawling skeleton of the universe. It is a reminder that scale can be deceptive, and that the seeds of greatness are often planted in the humblest of places. When you look up at the stars, it can be easy to think of them as eternal fixtures, but their very existence rests on the fact that the early universe was not perfectly smooth. It was not a flawless canvas, but one with faint brushstrokes running through it. Those brushstrokes became rivers of matter, flowing over time into the cosmic web. The galaxies we see today are like bright beads strung along those ancient ripples. Every light in the night sky is, in a way, a memory of the universe's restless beginning. The ripples in nothing may sound like a fragile foundation, but they were enough. Enough for gravity to begin its patient work. Enough to turn silence into structure. enough to give the cosmos a skeleton it would spend billions of years filling in. From quantum jitter to galaxies, the story begins with these wrinkles, and their quiet persistence is written across the sky we see each night. When we talk about the shape of the universe, it is tempting to imagine that what we see is what we get. Stars twinkling, galaxies spiraling, nebulae glowing faintly against the dark. Yet all of that dazzling scenery is little more than the garnish on a much larger dish. The real architecture of the cosmos is sculpted by something invisible, something that does not shine, flicker, or glow. This mysterious presence is known as dark matter, and without it, the cosmic web would never have taken shape. The idea of dark matter might sound exotic, but the reasoning behind it is surprisingly straightforward. Astronomers noticed long ago that galaxies were misbehaving. In the 1930s, Fritz Zwicky studied a cluster of galaxies called the Coma Cluster. He found that the galaxies were orbiting around their shared centre of mass far too quickly. According to the laws of gravity, based on the amount of visible matter present, the galaxies should have flown apart like sparks from a campfire, yet they clung together stubbornly. Zwicky proposed that there must be additional mass holding them in place, something invisible but heavy enough to provide the necessary gravitational glue. He called it Dunkel Materie, dark matter. Decades later, astronomer Vera Rubin confirmed a similar puzzle within individual galaxies. She studied how stars orbit around the centres of spiral galaxies, expecting to see the outer stars moving more slowly than the inner ones, much like planets around the Sun. Instead, she found that the rotation curves of galaxies were flat. The outer stars were moving just as quickly as the inner ones, as though each galaxy was wrapped in an enormous unseen halo of extra mass. Once again, the only sensible explanation was the presence of matter we could not see. Today, multiple lines of evidence point to the same conclusion. The universe is dominated by this invisible scaffolding. In fact, about 85% of all matter in the cosmos is dark matter. Ordinary matter, the atoms that make up stars, planets, oceans, and people, accounts for only a tiny fraction of the total. In other words, the stuff we can see is just the tip of the iceberg. The true bulk of the universe is hidden below the surface. What exactly is dark matter? That remains one of the biggest mysteries in physics. It does not emit light, absorb light, or reflect light. It does not interact strongly with normal matter in the ways we are used to. If you filled a jar with dark matter, it would pass right through the walls, the table, and even the floor, slipping silently toward the Earth's core. And yet, despite its ghostly nature, dark matter does interact with one thing very strongly: gravity. That gravitational pull is what sculpts the web of the universe. To picture dark matter's role, imagine building a city. First, you lay down an invisible framework of roads, intersections, and highways. The buildings, parks, and houses will later cluster around that structure. In the same way, dark matter provided the blueprint for the cosmic web. Its filaments stretched across the early universe, shaping where ordinary matter could gather. Gas flowed along the threads of dark matter, pooling in the densest knots to ignite stars and form galaxies. Without that hidden scaffolding, matter would have been too evenly spread out, unable to clump into anything as grand as a galaxy. Astronomers can actually see the effects of this invisible substance by watching how it bends light. According to Einstein's theory of general relativity, gravity curves space-time, and that curvature bends the path of light. When light from a distant galaxy passes by a large clump of dark matter, the galaxy's image is distorted, magnified, or stretched into strange arcs. This effect, called gravitational lensing, acts like a cosmic fingerprint for dark matter. By mapping those distortions, scientists can trace the otherwise invisible web. The results are astonishing. Filaments and halos of unseen matter crisscrossing the universe, with luminous galaxies dangling from them like dewdrops on a spider's thread. Another clue comes from the cosmic microwave background. The tiny temperature fluctuations in that ancient light encode the density of matter in the early universe. When physicists run the numbers, they find that the amount of ordinary matter is nowhere near enough to explain the patterns we see today. Only by adding dark matter to the equations does everything line up. The ripples from the beginning demanded a hidden mass to grow into the web we observe. Computer simulations provide perhaps the most striking evidence. Feed the laws of physics into a supercomputer, set the initial conditions based on the early universe, and then let it run. When dark matter is included, the result is a stunningly accurate cosmic web, filaments, voids, and clusters, just like we see in real surveys. Run the same simulation without dark matter, and the result is underwhelming. The universe remains too smooth, too bland, with no great threads forming. Reality seems to insist dark matter is the invisible architect. Despite this overwhelming evidence, the nature of dark matter remains elusive. Many scientists suspect it is made of exotic particles, perhaps weakly interacting massive particles, sometimes called WIMPs, or maybe axions, which are hypothetical particles born in the earliest moments after the Big Bang. Countless experiments buried underground, floating in balloons, or orbiting in satellites have searched for a direct detection of dark matter particles, but so far the universe keeps its secret. For now, dark matter remains the universe's greatest game of hide-and-seek. It is strange to think that most of the matter in the cosmos is invisible to us. When you look at the night sky, all the stars, planets, and glowing clouds are just the frosting on a cake we cannot see. Dark matter provides the sponge underneath, holding the whole thing together, even if it never catches the light. It is a humbling reminder that reality is not obligated to be visible to human eyes. In fact, most of it is not. Still, dark matter is not completely unknowable. While it refuses to shine, it reveals itself through its influence. It is the reason galaxies do not unravel, the reason clusters remain bound, the reason filaments stretched across billions of light years can hold their form. It is gravity's silent ally, pulling matter into place while remaining unseen. The cosmic web is not just made of galaxies, it is woven on dark matter's loom. In a way, this invisible mass makes the universe more intriguing, not less. Imagine if everything in the cosmos was simple, obvious, and directly visible. How dull it would be. Instead, we live in a universe with hidden layers, where the most important ingredients are the ones we cannot touch or see. Dark matter is not just an astrophysical oddity, it is a reminder that mystery itself is a fundamental part of existence. When you gaze at the stars, it's easy to think of them as the main characters in the story of the universe, but in truth, they are more like actors following a script written by an unseen hand. Dark matter shapes the stage, lays down the plot, and directs the action. The stars, the galaxies, and even we ourselves are following the quiet choreography of an invisible partner. The cosmos, then, is not just luminous, it is shadowed, scaffolded by something unseen. Dark matter's grip is firm but gentle, guiding matter into place without ever revealing its face. It is the silent skeleton of the universe, the unseen threads that hold the web together. And though we may never see it directly, its presence is undeniable, woven into the very fabric of the night sky. Gravity is often imagined as a dramatic force, pulling apples from trees or planets into orbit. But in the early universe it worked with far more patience. It did not fling matter into action in sudden bursts. Instead, it acted as a quiet sculptor, tugging ever so gently at the small ripples left over from inflation and dark matter's hidden scaffolding. Over vast stretches of time, those subtle pulls grew stronger, coaxing particles and gases into filaments that would one day thread across the cosmos. At first, the universe was filled with a nearly uniform fog of hydrogen and helium. No stars lit the darkness, no galaxies twirled their spiral arms, yet hidden beneath the apparent smoothness were slight variations in density. Where matter was just a fraction thicker, gravity had a little more to work with. those tiny differences became gravitational traps, slowly pulling in more gas, more particles, more of everything around them. Like raindrops gathering into rivulets, those regions became the foundations of cosmic structure. What is striking about gravity's role is how democratic it is. Every particle in the universe exerts a gravitational pull, no matter how small. A lone proton has its own gravity, although it is unimaginably weak. Multiply that by trillions upon trillions upon trillions of particles, and the effect becomes profound. Gravity has no off switch. It is always on, always reaching out across space. Even over billions of light years its influence stretches, gathering matter like an invisible net. As these slight overdensities grew, they began to stretch out into patterns. Instead of clumping into perfect spheres, the matter collapsed anisotropically, a word meaning unevenly, with different rates along different directions. This is where the magic happens. If gravity had drawn everything together uniformly, the universe might have been filled with isolated blobs of matter. Instead, because of the underlying dark matter scaffolding and the subtle variations in density, matter collapsed more easily in one direction than another. This uneven pull funneled matter into sheets, then into elongated filaments, like dough being rolled into strands. Those strands became the highways of the cosmic web. Computer simulations give us a front row seat to this process. Begin with a nearly uniform distribution of matter, add the small ripples from the early universe, and let gravity do its work. Over millions of simulated years, matter does not fall straight inward. It streams along invisible gradients. Dense regions pull matter from their surroundings, but the flow is directional. Over time, you see matter sliding into sheets, then threads, then nodes at the intersections. It looks uncannily like veins spreading through a leaf, or streams carving a watershed. The natural world loves patterns, and gravity seems to be its artist in chief. On human timescales, this work is imperceptible. A galaxy cluster does not grow like a flower blossoming overnight. Instead, it takes billions of years for gravity to tug matter into position. Imagine watching a glacier flow, barely moving to the naked eye, yet shaping valleys and mountains over millennia. Gravity's hand is even slower, but given enough time, it rearranges the entire universe. The patience is staggering. A web spanning billions of light years was drawn not with speed but with persistence. The elegance of this process lies in how gravity amplifies differences. A region just slightly denser than its surroundings becomes a little stronger gravitationally. That extra strength pulls in more matter, which makes it denser still, which increases its pull, and so on. This feedback loop snowballs until vast filaments take shape. Meanwhile, regions with slightly less matter lose even more as their contents drain away toward denser areas, leaving behind enormous voids. The cosmic web is born not from deliberate design, but from gravity's ability to take the faintest imbalance and exaggerate it into a grand structure. Observational evidence shows us the results of this process today. Large-scale galaxy surveys map out millions of galaxies, and when the positions are plotted, they do not appear randomly sprinkled. Instead, they fall into patterns of long strings and walls, exactly what simulations predict from gravity's steady hand. The largest structures we observe, colossal sheets of galaxies stretching hundreds of millions of light years, are monuments to gravity's quiet insistence. There is a certain poetry in how gravity draws these threads. It is not forceful in the way of a hammer striking metal. It is more like water wearing down stone, a gentle persistence that reshapes everything over time. The cosmic web is not a sudden creation but a slow weaving, with filaments drawn out of chaos like strands pulled from wool. At the heart of it all is nothing exotic or unfamiliar. Gravity is the same force that holds your feet to the ground and keeps the moon in orbit. The only difference is scale and patience. Consider how this perspective reframes the night sky. Every galaxy you see is not just floating aimlessly in the dark. It is bound along a filament, a luminous bead on a thread stretched across space. Those threads are not random. They were traced by gravity's hand billions of years ago, guiding matter into highways that shaped the universe's grand design. The Milky Way itself, with its 100 billion stars, owes its place in the cosmos to this invisible flow. We're inhabitants of a filament, part of a thread woven long before Earth was born. If gravity had been weaker, none of this would have happened. The early ripples would have remained mere ripples, never amplified into structure. If gravity had been stronger, the web would have collapsed too quickly, crushing matter into black holes and leaving little room for galaxies to breathe. The cosmic web exists in that narrow, delicate balance where gravity is just right, strong enough to gather matter, gentle enough to let it evolve into the structures we see today. In many ways, gravity is less like a dictator and more like a patient gardener. It does not impose order by force, but cultivates it over time, coaxing matter into patterns that emerge naturally. The filaments of the cosmic web are like vines trained along a trellis. The trellis is dark matter, but it is gravity that persuades the vines to follow it, that encourages galaxies to bloom where threads meet. When we step back and look at the universe as a whole, it is hard not to be struck by the beauty of this process. Out of a nearly featureless fog, gravity has spun lacework. Out of randomness, it has sculpted geometry. The web is a reminder that the cosmos is not static but dynamic, forever shaped by invisible hands pulling gently across unimaginable expanses of space and time. Gravity's role in drawing the threads of the cosmic web is both humbling and inspiring. It shows us that the universe did not need violence or chaos to craft its grandest structures. All it needed was time, patience, and a quiet force that never relents. The filaments stretching across billions of light years are monuments to persistence, proof that even the gentlest of tugs, given enough time, can redraw the face of the cosmos. If the cosmic web is a vast network stretched across the universe, then its most striking features are the intersections, the places where threads converge into luminous knots. These are the nodes, the cosmic hubs where gravity has pulled matter together in enormous concentrations. Within these nodes, galaxies gather in the thousands, stars are born in great numbers, and the universe feels most alive with activity. Imagine driving across a country on highways that stretch for hundreds of miles. The open road is quiet and sparse, but eventually you reach a city, a bustling convergence of roads, railways, and trade. The nodes of the cosmic web are like those cities. The filaments serve as highways funneling matter inward, while the nodes act as cosmic capitals, dense with galaxies bound tightly by gravity. The scale of these hubs is staggering. A single galaxy cluster, the basic unit of a node, can contain anywhere from hundreds to several thousands of galaxies. Each of those galaxies may have billions of stars, and many of those stars may host planets. Surrounding the galaxies is a halo of dark matter, along with vast pools of superheated gas that glow faintly in X-rays. Clusters are the most massive gravitationally bound structures in the universe, weighing in at quadrillions of times the mass of the Sun. They are the heavyweights of cosmic architecture, where the web's threads tie themselves into dense knots. One of the most famous clusters is the Coma Cluster, located about 300 million light-years away. Discovered more than a century ago, it contains thousands of galaxies packed into a relatively small region of space. When astronomers look at it, they see not just a random swarm, but a family bound together by an invisible hand. Every galaxy inside the cluster is orbiting around the cluster's centre of mass, moving at incredible speeds but never escaping. It is like a cosmic beehive, busy, crowded, and tightly held by gravity. At the very heart of galaxy clusters often lie giant elliptical galaxies, some of the largest single galaxies in existence. These titans form through repeated mergers, as smaller galaxies streaming along filaments crash into the hub and combine. Over time, the central galaxy grows bloated and luminous, becoming the anchor of the cluster. It sits there like the king of the hill, while smaller galaxies swirl around it, their paths determined by the gravitational choreography of the node. The filaments that feed these clusters are just as important. They act as supply lines, channeling gas and galaxies into the hubs. Without them, the clusters would starve. The cosmic web is not static. Material continues to flow along the filaments like rivers feeding into a lake. Astronomers call this process cosmic accretion. As matter streams along the threads, clusters grow larger, galaxies collide more frequently, and stars ignite in bursts of activity. Clusters and filaments also provide a natural laboratory for the extremes of physics. The gas trapped in these regions is heated to tens of millions of degrees, hot enough to emit X-rays detectable by orbiting telescopes. Within the crowded environment, galaxies interact more often, tugging on each other's shapes, stripping gas, and sometimes merging entirely. These interactions shape the evolution of galaxies in ways that isolated ones never experience. Life in the hub is crowded and competitive, while life out on the filaments is quieter, more solitary. Another fascinating aspect of these nodes is how they connect to form even larger structures. Galaxy clusters rarely exist alone. They gather into superclusters, immense regions containing multiple clusters linked by filaments. The Virgo supercluster, for example, is our local home, stretching more than 100 million light-years across and containing the Virgo cluster along with our own Milky Way. Even this, however, is just one piece of a larger structure called Laniakea, a supercluster spanning 500 million light-years, with hundreds of thousands of galaxies bound together in a gentle gravitational embrace. Our galaxy is just one faint light in a corner of this colossal cityscape of matter. The nodes of the cosmic web reveal another remarkable truth. The universe is hierarchical. Small structures form first, then combine into larger ones. Tiny ripples of matter grew into galaxies, galaxies gathered into clusters, clusters linked into superclusters, and superclusters stitched themselves into the great web. It is a nested Russian doll kind of cosmos, with each level supported by the scaffolding of dark matter and the patient hand of gravity. The nodes are simply the places where this hierarchy is most visible, where the scale of matter's ambition is on full display. Astronomers are continually mapping these intersections with greater precision. Using gravitational lensing, redshift surveys, and X-ray observations, they can trace where matter is piling up in the web. The resulting maps are not random splashes of light, but intricate patterns of nodes connected by glowing strands. They look almost biological, as though the universe itself were alive, its galaxies the neurons of a vast cosmic brain. The resemblance between the cosmic web and neural networks has inspired endless comparisons, though in truth, one is made of stars and the other of cells. Still, it is hard not to notice the similarity when you see a map of the web and a scan of the human brain side by side. These intersections also remind us how fragile cosmic balance can be. A cluster is held together by gravity, but it is constantly fighting the universe's expansion, which tries to pull everything apart. Dark energy, the mysterious force driving this expansion, works against the clustering of matter. Yet for now, clusters and nodes remain intact, the gravitational anchors of the web. Billions of years from now, their supply lines may run dry as the expansion accelerates, but in the present, they stand as the universe's bustling downtowns. When you look at a starry sky from Earth, it is easy to feel alone, like islands scattered in an endless sea. But nodes remind us that the universe is communal. Galaxies are not drifting aimlessly. They are gathered into neighbourhoods, districts and cities, bound together in a web of connections. The Milky Way belongs to one of these neighbourhoods, linked by filaments to others, all converging toward larger nodes. We are part of a vast and ancient network, not an isolated outpost. The cosmic web, with its nodes and filaments, is a portrait of gravity's social instincts. Matter does not like to be alone. It prefers to gather, to connect, to form hubs where activity thrives. The nodes are where the story of structure reaches its loudest crescendo, with galaxies clustering in their thousands, colliding, merging and shining. They are reminders that the universe is not only vast and empty, but also alive with bustling centres of matter, each a city of galaxies linked by threads across the deep. What may be most striking of all is how much of this is invisible. The galaxies themselves are like the glowing streetlights of the cosmic city, but most of the mass, the dark matter scaffolding, remains unseen. The true structure is hidden, revealed only through its influence. Yet even without seeing it directly, we know it is there, pulling matter into place, stitching galaxies into clusters, and tying the entire cosmos together. To drift among the nodes is to witness the universe at its most energetic, its most social, and its most connected. These hubs are the knots in the cosmic net, places where the threads of the universe tie themselves into luminous gatherings. From the smallest galaxies to the grandest superclusters, they are all beads strung on filaments, bound by gravity and woven into the architecture of the cosmos. If the nodes and filaments of the cosmic web are its luminous highways and bustling cities, then the voids are its deserts, vast stretches of almost nothing, where galaxies are scarce and silence reigns. At first thought, emptiness may not sound like much of a story, but in truth the voids are as essential to the web as the threads themselves. Without the empty, there would be no contrast to the filled. The universe's great architecture is defined not only by what is there, but also by what is not. These voids are enormous. A typical cosmic void can span tens of millions of light years across, and the largest can stretch well over 100 million. Imagine a sphere so large that if you placed our Milky Way galaxy at its centre, every single galaxy we can see with the naked eye in the night sky would fit inside comfortably, with room to spare, and yet the void would still look mostly barren. There are regions where gravity has drained matter away, pulling it along invisible slopes into the filaments and nodes nearby, leaving behind vast hollows in the cosmic landscape. One of the earliest surprises of modern cosmology came in the 1970s and 80s, when astronomers first began mapping galaxies in 3 dimensions. They expected to see a fairly even distribution, perhaps with a few clumps here and there. Instead, they saw striking patterns, long chains and walls of galaxies surrounding enormous empty spaces. These voids were not small gaps. They were the dominant feature. The web of the universe, it turned out, is as much about the hollow regions as the luminous structures outlining them. The largest known example is the Bhuta's Void, discovered in 1981. It is a gargantuan stretch of near nothing, roughly 330 million light-years across. For comparison, that is about 3,000 times the diameter of our own Milky Way. Within it, only a handful of galaxies have been found, lonely outposts scattered through the dark. To drift through the Bhuta's Void would be to experience an almost unthinkable isolation, hundreds of millions of years of travel in any direction, without encountering more than the rare flicker of starlight. Yet voids are not truly empty. They contain dark matter, thin traces of hydrogen gas, and the occasional solitary galaxy. They are underdense rather than vacant, with perhaps only 10% of the average cosmic density. This might not sound like much, but it is enough to matter. The leftover gas within voids is often too thin to collapse into stars, so these regions remain faint and quiet. It is as though they are the quiet backwaters of the cosmos, bypassed by the great flows of matter streaming into the web's threads. Galaxies that do exist in voids tend to be unusual. With fewer neighbours to disturb them, they evolve more slowly, retaining their gas for longer periods of time. Some are small and irregular, forming stars at a leisurely pace. Others are surprisingly isolated spirals, like lonely pinwheels turning in the dark. Studying these galaxies is a challenge, but it also provides insight into how environment shapes cosmic evolution. A galaxy in the middle of a busy node may grow rapidly through collisions and mergers, while one in a void evolves in near solitude, shaped only by its own internal processes. Voids also play an important role in cosmology. by acting as natural laboratories for dark energy. Because they are underdense, they expand faster than the universe as a whole. This accelerated expansion exaggerates the influence of dark energy, making voids sensitive indicators of its strength. By studying how galaxies are distributed within and around voids, astronomers can refine their understanding of how dark energy drives the universe's growth. The emptiest places, it seems, can sometimes speak the loudest about the fate of everything. On a more poetic level, the existence of voids changes how we imagine the cosmos. Without them, the universe would be an unbroken wall of galaxies, crowded and overwhelming. Instead, it is a balance of fullness and emptiness, light and dark, structure and silence. The web's beauty comes from contrast, the way threads of matter stand out precisely because of the hollows around them. Like lacework or foam on the crest of a wave, the cosmic web is defined as much by its holes as by its strands. Drifting through a void, one would feel a sense of vast stillness. No nearby galaxies blazing with billions of suns, no clusters buzzing with activity, just the faintest background glow of the universe itself. It would be the ultimate quiet, an expanse where the nearest galactic neighbour could be hundreds of millions of light years away. And yet, even in that quiet, gravity would still be at work. Over cosmic timescales, the emptiness deepens as matter continues to flow outward, feeding the filaments at the edges. The voids are not passive, they are dynamic, slowly emptying further as the universe evolves. Voids also influence the motion of galaxies on their borders. Just as clusters pull galaxies inward, voids push them outward. Not through any mysterious repulsive force, but simply because galaxies on the edge of a void feel stronger, gravitational pulls from the denser regions beyond than from the empty interior. In this way, voids act as silent sculptors, shaping the flows of matter at the larger scales. Even the human imagination struggles with the enormity of such hollows. When we describe them as empty, we're using the word loosely. They are not blank like a sheet of paper, but more like a faded watercolour, where the brushstrokes have thinned to almost nothing. For many, there is something unsettling about the idea of so much nothingness, but in another sense, it is comforting. The voids are space for the web to breathe. They are reminders that the universe is not overcrowded, that even at the larger scales it holds vast expanses of quiet and calm. The story of cosmic voids is not one of absence, but of balance. The nodes and filaments may get the attention with their dazzling galaxies, but without the voids there would be no web to admire. The hollows make the structure stand out. They are the spaces between the notes, the silence that allows the music of the universe to be heard. The cosmic web is not just a network of matter, it is a dance of presence and emptiness, woven together into the grandest pattern we know. Mapping the universe is no simple task. Unlike an ordinary landscape, there are no landmarks you can stroll up to and measure directly. The cosmic web does not announce itself with street signs or borders. Its filaments and nodes are invisible to the naked eye, drawn not in light but in gravity. And yet astronomers have found ways to chart these hidden structures, turning the night sky into a kind of navigable map. These are the cosmic cartographers, the scientists who trace patterns too vast to imagine, using clever methods to reveal the skeleton beneath the stars. The first challenge in making such a map is deceptively simple: distance. Looking at the sky tells you the position of a galaxy in 2 dimensions. You can say it is up near this constellation or down near that one. But to understand the web, you need to know how far away it is. Without distance, the universe looks like a flat painting, beautiful but misleading. The trick to unlocking the 3rd dimension is redshift. When light travels through an expanding universe, its wavelength is stretched, shifting it toward the red end of the spectrum. The farther away a galaxy is, the more its light is stretched. By carefully measuring this redshift, astronomers can determine how far the galaxy has travelled from us, and by extension, how far away it currently lies. It's a bit like hearing the pitch of a siren change as an ambulance moves away, except the siren is a galaxy, and the pitch has been stretched across millions or billions of years. Armed with redshift measurements, astronomers began assembling three-dimensional maps of galaxy positions. What had once looked like a random sprinkle of light suddenly revealed astonishing order. Instead of being scattered evenly, galaxies lined up in long strings and walls, leaving behind enormous voids. The cosmic web was no longer theory, it was charted territory. Early surveys, though small by today's standards, hinted at this structure. In the 1970s, projects like the CFA Redshift Survey began to plot galaxies not just across the sky, but in depth. As the data accumulated, astronomers realized they were seeing something entirely new. The universe had texture. Those first maps looked almost like coral, with branching structures and hollow bubbles. They were glimpses of the web that underlies everything. As technology improved, surveys expanded in scope. The Sloan Digital Sky Survey, launched in the late 1990s, revolutionized our view of the cosmos. Using a dedicated telescope in New Mexico, it has measured redshifts for millions of galaxies, producing a three-dimensional atlas of unprecedented detail. When astronomers visualize the results, they see filaments stretching across hundreds of millions of light years, knots where clusters gather, and yawning voids in between. For the first time, humanity could see the web not as a vague concept, but as a mapped reality. These maps are not just pretty pictures, they are scientific gold mines. By studying the distribution of galaxies, astronomers can test theories of dark matter, dark energy, and cosmic evolution. For example, the spacing of galaxies reveals something called baryon acoustic oscillations, subtle imprints of sound waves that rippled through the early universe's plasma. These oscillations act as a kind of standard ruler, allowing cosmologists to measure the expansion history of the universe with remarkable precision. In other words, galaxy maps are not just charts of where things are, but also time capsules telling us how the universe has grown. Of course, redshifts are not the only tool. Astronomers have developed other ingenious methods to trace the invisible patterns. One approach is gravitational lensing, where the gravity of dark matter bends light from more distant galaxies. By studying how galaxy shapes appear stretched or warped, astronomers can infer the presence of massive, unseen structures. In this way, they can draw maps of dark matter itself, rather than just the galaxies riding on top of it. It is a bit like seeing the wind by watching the way trees sway, even if the wind itself is invisible. Another clever method involves looking at the faint absorption lines in the spectra of distant quasars. As the light from these bright ancient beacons passes through intervening gas, it picks up subtle marks, like fingerprints of the material it travelled through. By comparing multiple quasar lines of sight, astronomers can reconstruct the distribution of hydrogen gas across cosmic scales. This technique, known as the Lyman alpha forest, provides another way to sketch the hidden filaments of the web. Taken together, these techniques form a toolbox of cosmic cartography. Each method offers a different perspective, like layering maps of roads, rivers, and elevation on top of one another. Redshift surveys show where galaxies gather, lensing reveals the dark matter scaffolding, and quasar absorption traces the thin gas connecting it all. Piece by piece, the invisible becomes visible. It is worth reflecting on the scale of these maps. On Earth, cartography is a matter of miles or kilometers. Even the largest global maps cover a planet only about 40,000 kilometers around. Cosmic cartographers, by contrast, deal in millions of light years. A single filament can stretch across 500 million light years. A void can span 100 million. These maps are not of continents or oceans, but of structures so large they defy ordinary imagination. And yet, through careful observation, scientists have turned them into something we can hold in our minds. There is also a certain elegance in how these maps blur the line between science and art. Visualizations of the cosmic web are among the most beautiful images in astronomy. Glowing networks of light that resemble lace, coral, or neurons. They are not just scientific products but works of cosmic art, revealing patterns that seem almost designed for aesthetic wonder. In truth, they are the natural result of gravity's slow hand and dark matter's scaffolding, but their beauty is undeniable. What makes cosmic cartography especially remarkable is that it is ongoing. Every new survey adds depth, clarity, and reach. The Dark Energy Spectroscopic Instrument, for example, is now measuring redshifts for tens of millions of galaxies, building the largest three-dimensional map ever attempted. With each new effort, the cosmic web becomes sharper, its filaments more defined, its voids more pronounced. We are still in the early stages of mapping the full skeleton of the universe, and the journey ahead promises even greater revelations. In the end, these cosmic maps are more than technical achievements. They're acts of human curiosity, attempts to take something unimaginably vast and render it comprehensible. They remind us that even when faced with distances measured in billions of light years, we can still find patterns, structure, and meaning. The universe is not a chaotic scattering of galaxies but a woven tapestry, and through cleverness and patience we have learned to trace its threads. To hold such a map in your mind is to see the universe in a new light, no longer as a flat dome of stars, but as a living network of filaments and nodes stretching into the deep. Cosmic cartographers have given us the gift of perspective, a reminder that we are not adrift in randomness but connected through a vast and hidden architecture. It is a map that shows not where we are going, but where we belong. At the turn of the new millennium, astronomers began an ambitious project that would change how humanity sees the universe. It was called the Sloan Digital Sky Survey, often shortened to SDSS, and it set out with a bold goal: to create the most detailed three-dimensional map of the cosmos ever attempted. For centuries, star charts had guided sailors and explorers across Earth's oceans, but the Sloan map would guide us across the oceans of space. Instead of plotting coastlines and islands, it would chart galaxies, clusters, and the hidden patterns of the cosmic web. The Sloan project was named after Alfred P. Sloan, whose foundation funded much of the effort. The telescope itself, a dedicated 2.5-meter instrument at Apache Point Observatory in New Mexico, was purpose-built for wide-field surveys. Unlike many telescopes that peered deeply into one small patch of sky, this one was designed to sweep across vast areas, systematically cataloguing stars and galaxies. Equipped with advanced digital detectors, it could record hundreds of spectra at once, allowing astronomers to measure distances for an unprecedented number of celestial objects. In the early days, there was a sense of anticipation, almost of audacity. Could a single survey really capture a meaningful portion of the universe in detail? The answer came swiftly, and it was resounding. As the data rolled in, astronomers began to assemble the largest atlas of the universe ever made. Over the years, the Sloan survey would collect redshifts for millions of galaxies, transforming the night sky from a flat sprinkling of lights into a dynamic three-dimensional structure. When the first results were visualized, they stunned the scientific world. The galaxies were not scattered like sand on a beach, but arranged in patterns of filaments, walls, and voids. In particular, one of the earliest slices of the Sloan map revealed an enormous concentration of galaxies known as the Sloan Great Wall, a structure stretching over 1.5 billion light-years across. To put that in perspective, light itself, moving at nearly 300,000 kilometers per second, would take over 1.5 billion years to cross from one side of the wall to the other. It was one of the largest coherent structures ever discovered, and it stood as direct evidence of the web-like nature of the cosmos. The power of the Sloan survey lay not just in its scale, but in its precision. With accurate redshift measurements, astronomers could place each galaxy in 3 dimensions, revealing not only its location but also its relationship to its neighbours. Suddenly, the cosmic web was no longer theoretical, no longer inferred from patchy observations. It was there on the screen, a glowing lattice stretching across billions of light years. Clusters shone like knots, filaments threaded between them, and yawning voids gaped in between. The Sloan map also helped cosmologists tackle some of the biggest questions in physics. By measuring the clustering of galaxies, the survey detected subtle ripples called baryon acoustic oscillations, the faint echoes of sound waves that rippled through the hot plasma of the early universe. These ripples left an imprint on the distribution of galaxies, providing a standard ruler to measure cosmic distances. With this tool, scientists could track how the universe's expansion has changed over time, offering crucial insights into the mysterious force of dark energy. Beyond its headline discoveries, the Sloan survey became a workhorse of modern astronomy. Its publicly available data empowered countless research projects. From mapping the Milky Way's structure to cataloguing quasars and distant galaxies, the Sloan database became a treasure trove for scientists worldwide. In fact, it is often said that the Sloan Digital Sky Survey is the most scientifically productive, astronomical project in history, cited in more papers than almost any other telescope. Part of its success lies in the philosophy of openness. Unlike many observatories where data is tightly guarded for years, Sloan made its maps and spectra available to the entire community on a regular basis. Students, amateur astronomers, and professional scientists alike could dive into the data, exploring the universe from their laptops. This democratization of cosmic cartography accelerated discoveries in ways no one fully anticipated. The Sloan map also reshaped how we visualize the universe. When astronomers first plotted its galaxy data in a slice of the sky, it resembled a fan or wedge stretching outward from Earth. Each dot represented a galaxy, and together they traced out filaments and voids like coral branches radiating in all directions. These images quickly became iconic, appearing in textbooks, lectures, and planetarium shows. They conveyed in a single glance that the universe is not a random spray of galaxies, but a structured, interconnected web. Perhaps what is most remarkable is how the Sloan map gives us a sense of belonging in the cosmos. It is one thing to know that the Milky Way sits in a galaxy cluster, which sits in a supercluster, which is part of a greater web. It is another to see it plotted on a map, to know our place in the grand pattern. The Sloan survey gave humanity a cosmic address, not just as residents of Earth or the Milky Way, but as part of the Laniakea supercluster, woven into filaments stretching for hundreds of millions of light years. Of course, the Sloan map is not the final word. It is a snapshot, a first draft of cosmic cartography. Newer projects like the Dark Energy Spectroscopic Instrument and the Euclid mission are expanding the map further, adding more galaxies, greater depths, and sharper detail. Yet Sloan remains a landmark, the survey that first revealed the web in a way anyone could see and grasp. It was the breakthrough that turned speculation into structure, theory into an atlas. There is something profoundly moving about looking at a Sloan map visualization. Each dot is a galaxy, each galaxy is a city of stars, and each star may host worlds of its own. And yet, when plotted together, they form threads and walls, as though the universe itself were weaving. It is both humbling and inspiring. Humbling because of the immensity, inspiring because we have found a way to see it. The cosmic web may be invisible to the eye, but with the Sloan Digital Sky Survey, humanity sketched its outline and revealed the architecture of the universe. In the end, the Sloan map is not just data. It is a story of curiosity, persistence, and vision. It shows that with the right tools, the invisible can become visible, the unimaginable can be charted, and even the universe itself can be mapped. For the first time in human history, we have a chart of the web that holds us, and it is a map not of seas or continents, but of the skeleton of the cosmos. Light, for all its speed and grace, is not entirely free. It may race across billions of light years, but the path it takes can be bent, twisted, and reshaped by gravity. This bending of starlight is one of the strangest and most beautiful predictions of Einstein's general theory of relativity. It is also one of the most useful tools astronomers have for uncovering the invisible scaffolding of the cosmos. By studying how light curves as it passes massive structures, scientists can map dark matter, revealing the hidden threads of the cosmic web. This technique is called gravitational lensing, and it is gravity's fingerprint on the fabric of the universe. To understand the idea, imagine holding a magnifying glass over a page of text. The words bend and stretch as the lens redirects the light. Gravity acts in a similar way, except the lens is not made of glass, it is made of mass itself. A galaxy, a cluster, or even a filament of dark matter can warp space-time, curving the trajectory of light passing near it. To an observer, the background galaxy appears distorted, magnified, or sometimes even duplicated as though seen through a cosmic funhouse mirror. This was not always an accepted idea. Before Einstein, Newtonian physics described gravity as a force pulling directly between objects. It could keep planets in orbit, but it had nothing to say about the bending of light. In 1915, Einstein proposed that gravity is not a pull at all, but a curvature of space-time. Massive objects act like heavy spheres placed on a stretched sheet, warping the surface so that anything moving across it follows a curved path. Light, though massless, still travels through space-time and therefore feels its curves. The first confirmation came in 1919, when astronomers measured the positions of stars during a solar eclipse. They found that starlight passing near the sun was bent by exactly the amount Einstein had predicted. The news made him a household name overnight. Since then, gravitational lensing has become one of the most powerful techniques in astronomy. There are two main varieties. Strong lensing occurs when a massive object, such as a galaxy cluster, lies directly in front of a more distant galaxy. The foreground mass bends the background light so dramatically that it can create multiple images, arcs, or even complete rings of light known as Einstein rings. These striking patterns are like neon signs advertising the presence of invisible mass. Weak lensing, by contrast, is more subtle. Here the distortions are tiny, not easily visible in a single galaxy. But by studying the shapes of millions of galaxies, astronomers can detect statistical patterns of stretching that reveal the presence of dark matter. It is a bit like looking at a forest in the wind. A single leaf may not tell you much, but when all the leaves lean the same way, you know the air is moving. Similarly, weak lensing shows the collective tug of unseen matter shaping the background light. By applying these techniques, astronomers have created detailed maps of dark matter across the sky. One of the most famous examples came from the Hubble Space Telescope, which used weak lensing to reveal sprawling dark matter filaments connecting galaxy clusters. These filaments match the predictions of computer simulations, confirming that dark matter really does form the skeleton of the cosmic web. It was like turning on a black light in a room and suddenly seeing the hidden patterns glowing on the walls. Perhaps the most dramatic demonstration of lensing's power comes from galaxy clusters. Take Able 1689, a massive cluster more than 2 billion light-years away. Images from Hubble show dozens of elongated arcs encircling the cluster. Each arc is the distorted image of a more distant galaxy, its light bent by the cluster's enormous gravitational field. By analysing the precise shapes and positions of these arcs, astronomers can calculate the distribution of dark matter within the cluster. The luminous galaxies and hot gas are just the surface decoration. The bulk of the mass lies in a sprawling, invisible halo of dark matter, traced only by the bent paths of light. Lensing has also played a key role in one of the most important cosmic experiments, the Bullet Cluster. This system, formed by two colliding galaxy clusters, provides striking evidence for dark matter's existence. When the clusters smashed together, their hot gas clouds collided and slowed, emitting X-rays. But gravitational lensing revealed that the bulk of the mass passed straight through with the galaxies, leaving the gas behind. This separation of normal matter and gravitational mass cannot be explained without dark matter. It is as though the cosmos performed its own experiment, peeling back the layers to show us what is truly holding the structure together. On larger scales, weak lensing surveys are mapping dark matter across billions of light years. Projects like the Dark Energy Survey and the Hyper Supreme Cam survey in Japan have charted enormous swaths of sky, revealing a cosmic web of dark filaments threading between clusters. Each faint distortion of a background galaxy adds one more brushstroke to the map until the hidden skeleton emerges in full. These surveys not only trace dark matter, but also test cosmological models. By comparing the observed web with simulations, scientists can refine their understanding of how the universe evolved. Lensing is not only useful for dark matter, it also magnifies distant galaxies, acting as a natural telescope. Strong lensing can boost the light from galaxies too faint to see otherwise, allowing astronomers to study the earliest galaxies formed just a few 100 million years after the Big Bang. In a sense, the universe provides its own zoom lenses, bending light in our favour. But for the story of the cosmic web, lensing's greatest contribution is the way it reveals the invisible scaffolding holding everything in place. What is remarkable is how elegant the method is. Light from distant galaxies has been travelling for billions of years, minding its own business, when suddenly it encounters a massive clump of dark matter. Its path curves like a runner taking a bend in the track, and it continues on toward Earth. By the time it reaches our telescopes, the image has been stretched or duplicated. That distortion is not a flaw, it is information encoded in the shape of light. Astronomers, acting as detectives, decode the message to reconstruct the invisible structures along the way. It is easy to forget how astonishing this really is. We're inferring the presence of vast unseen filaments of matter, not by touching them or seeing them directly, but by noticing the way they bend the light of galaxies billions of light years beyond them. It is like detecting the existence of wind, not by feeling it on your skin, but by observing a candle flame flicker in a distant window. The subtlety of the method underscores the ingenuity of human curiosity. Gravitational lensing is gravity's fingerprint, a mark left on the light that passes by. Each arc, each distortion, is a clue pointing to the hidden mass shaping the universe. Together, they form maps of the web, revealing a cosmos far richer and stranger than what our eyes alone can see. The stars and galaxies may shine, but it is the unseen matter, traced through bent light, that reveals the true design of the cosmic skeleton. And perhaps the most poetic part of all is this: the universe itself becomes the lens. Space and time, bent by mass, turn into tools of observation. The cosmos is not only the subject of our study, but also the instrument through which it shows itself to us. Through these curved paths of light, the hidden architecture of the universe is drawn into view, and the threads of the cosmic web are traced across the heavens. Galaxies are not sprinkled randomly through the universe like sugar scattered across a kitchen counter. Instead, they gather in long interconnected filaments, strung out like beads on invisible threads. These filaments are the highways of the cosmic web, and galaxies follow them faithfully, clustering where the strands intersect and thinning out toward the great voids. To understand why galaxies form along these threads, we must look at how matter flows in the universe, and how the web itself acts like a vast delivery system, channeling material into the places where galaxies can be born and thrive. The foundation of this pattern is gravity working on dark matter. Long before the first stars lit up, the universe was filled with an invisible scaffolding of dark matter filaments. These acted as funnels, directing gas into narrow streams. Hydrogen and helium, the primordial ingredients left over from the Big Bang, did not spread evenly in every direction, but instead slid down the gravitational slopes carved out by dark matter. Just as rainwater flows into rivers and rivers into valleys, so too did gas collect along these threads. The result was a cosmic plumbing system where gas was guided into filaments that served as the raw material supply lines for galaxies. The gas streaming along these filaments cooled and condensed, forming dense clouds that eventually ignited into stars. Where multiple filaments intersected, even more gas accumulated, creating galaxy clusters. In this way, the web acted as both the blueprint and the builder, dictating where galaxies would arise and how they would evolve. Without the guiding hand of the filaments, matter might have spread too thinly, never reaching the densities required to spark star formation. Computer simulations of cosmic structure formation make this process vividly clear. When astronomers model the universe with dark matter and gas, they see filaments emerge naturally. Gas flows along them like traffic on a busy highway, funneled into hubs where clusters of galaxies form. Galaxies within these simulations rarely appear far from the threads, confirming that the cosmic web is not just background decoration, but the main organising principle of galactic life. Observations of the real universe match these simulations beautifully. Large-scale surveys show that galaxies overwhelmingly lie along filaments, rarely straying deep into the voids. Those few that do are lonely and often unusual in appearance, starved of fresh gas supplies. By contrast, galaxies along the threads are constantly fed by streams of material flowing through the web. This continuous resupply is critical for their growth, fueling star formation and sustaining them across billions of years. One of the fascinating consequences of this filamentary feeding is that galaxies are not just passively placed along the web, but actively shaped by it. Streams of cold gas funnel directly into galaxies, sometimes triggering starbursts as new material ignites. The orientation of galaxies can also be influenced by the filaments. Spiral galaxies, for example, often align their spin axes with the direction of the thread they inhabit. It is as if the galaxies know which way the road runs and orient themselves accordingly, joining the cosmic traffic. The web is not uniform, however. Some filaments are thick and bustling, packed with gas and galaxies, while others are thin and faint, barely detectable. The thickness and density of a filament determine the kind of galaxies that form along it. Thick, massive filaments tend to host larger galaxies and feed rich clusters, while thinner strands may only support smaller, more fragile systems. This variety is part of what gives the universe its diversity of galactic forms, from giant ellipticals to delicate spirals and irregular dwarfs. Clusters of galaxies at the intersections of filaments serve as dramatic demonstrations of this process. They are like major junctions on the cosmic highway, where multiple streams of material converge. These clusters are not static. They are still being fed by the filaments today. Galaxies continue to stream inward, sometimes colliding and merging, fueling bursts of activity. The supply lines never close, ensuring that the busiest parts of the cosmic web remain lively even in the present epoch. The flow of matter along filaments also explains why star formation has not yet completely died out in the universe. Although the overall rate of new star birth has slowed since its peak about 10 billion years ago, many galaxies are still forming stars thanks to a steady trickle of fresh gas arriving from the web. Without these cosmic supply lines, galaxies would have long since consumed their reserves and gone dark. The web is not just scaffolding, it is nourishment, delivering fuel that keeps the lights of the cosmos burning. In some cases, gravitational interactions within filaments can bring galaxies together. These encounters may trigger mergers, dramatically altering galactic structure and sparking waves of new stars. The filaments, then, are not only feeding galaxies but also orchestrating their interactions. A spiral galaxy drifting peacefully along a thread may one day find itself colliding with a neighbour, an event set in motion billions of years earlier by the flow of matter through the web. Astronomers studying these processes often draw analogies to ecosystems. Just as rivers, valleys, and fertile plains determine where plants and animals thrive on Earth, so the cosmic web determines where galaxies flourish in space. The voids are deserts, thin and empty, while the filaments are fertile river valleys, sustaining a rich variety of galactic life. The web is not alive in any literal sense, of course, but it functions like an environment, shaping the conditions under which galaxies form, grow, and evolve. There is also a philosophical beauty to this arrangement. Galaxies, with all their stars, planets, and potential for life, are not scattered haphazardly, but connected by invisible highways of matter. It is a reminder that even on the grandest scales, the universe is about relationships and connections. Each galaxy is part of a greater network, nourished by the threads that link it to countless others across billions of light years. To gaze at the cosmic web, whether through the lens of a computer simulation or the results of galaxy surveys, is to see the grand design of gravity and dark matter at work. The filaments are not just outlines on a map, but the very arteries of the cosmos, pumping material into galaxies and clusters, sustaining the universe's luminous heartbeats. Every star you see in the night sky was likely born thanks to these hidden highways, every galaxy a traveller on the filaments of the web. The threads of the cosmic web are both pathways and lifelines. They are the reason galaxies exist where they do, the reason clusters form at intersections, and the reason the universe has structure rather than formless chaos. They act as couriers of creation, delivering gas and matter along invisible routes, weaving galaxies into place. In the quiet majesty of the cosmic web, the galaxies strung along its threads are the bright jewels of a universe forever shaped by its hidden skeleton. On the grandest scales, the universe is not simply a collection of galaxies or even clusters of galaxies. It is stitched together into colossal formations that stretch across hundreds of millions of light years. These superclusters and walls are the largest coherent structures we know, vast gatherings of galaxies tied together by gravity and outlined by the filaments of the cosmic web. To look at them is to glimpse the true immensity of the cosmos, and to realize that even our home galaxy, large as it seems, is just a single note in an unimaginably vast symphony. One of the most important of these structures is our own neighborhood supercluster, known as Laniakea. The name, from the Hawaiian language, means immense heaven, and it is hard to imagine a more fitting description. Laniakea spans about 500 million light-years and contains over 100,000 galaxies, including the Milky Way. It is a region where countless filaments converge, all flowing toward a gravitational basin known as the Great Attractor, a mysterious concentration of mass that tugs galaxies from millions of light-years away. To put the size of Laniakea into perspective, consider this. If you could travel at the speed of light, it would take you 500 million years to cross from one side to the other. By comparison, Earth's entire history, from its formation to today, spans only about 4.5 billion years. In other words, you would need to cross Laniakea nearly 10 times just to cover the lifetime of our planet. And this is just one supercluster among many, one piece of the web's immense architecture. The discovery of Laniakea came from carefully mapping the motions of galaxies. Astronomers tracked how thousands of galaxies move relative to one another and found that their motions were not random. Instead, they flowed together like rivers converging on a basin. This basin defined the boundary of Laniakea, showing that our Milky Way and its neighbours are part of something far larger than the local group or even the Virgo cluster. We are strands in a cosmic current, drawn toward a gravitational destination we cannot yet see in full. Beyond our local neighbourhood, other superclusters show just how vast and varied the web can be. The Shapley supercluster, for instance, is one of the most massive concentrations of galaxies in the nearby universe. Located about 650 million light-years away, it contains more than 8,000 galaxies spread across dozens of clusters. Its immense gravity exerts a pull not just on its own galaxies, but on ours as well. The Milky Way, along with the rest of Laniakea, is slowly drifting in its direction, influenced by its titanic mass. The Shapley supercluster is like a heavyweight in the cosmic ring, pulling on everything nearby. Then there are the walls, the truly immense structures that stretch across cosmic surveys like barriers of light. One of the first and most famous is the Sloan Great Wall, discovered in 2003 using the Sloan Digital Sky Survey. This wall is a chain of galaxy clusters and superclusters stretching over 1.5 billion light-years across. It is one of the largest known structures in the universe, a luminous ridge of galaxies marking one of the densest regions of the web. If you could see it from outside, it might resemble a glowing sheet strung across the darkness, with filaments branching outward like roots or veins. These walls challenge our sense of scale. Galaxies, on their own, are already enormous, each containing billions of stars. Clusters of galaxies are vast enough to dwarf the imagination, but walls and superclusters extend the scale by orders of magnitude, weaving galaxies into tapestries that stretch nearly as far as we can measure. They are cosmic continents, with the filaments as their mountain ranges and the voids as their oceans. What is especially striking is how these colossal structures reveal the organizing principle of the universe. They are not random collections of galaxies. Their shapes and sizes match the predictions of cosmological models that include dark matter and dark energy. The web seems to follow rules laid down in the earliest moments after the Big Bang, with superclusters and walls arising as natural consequences of gravity, amplifying tiny fluctuations in the young universe. In other words, these grand designs are not accidents. They are the inevitable outcome of the cosmos stretching and clustering over billions of years. Astronomers often debate whether structures as large as the Sloan Great Wall can even be considered objects in the usual sense. Their sheer scale pushes the limits of what we expect from cosmic uniformity. On the largest scales, the universe is supposed to be homogeneous, meaning that no matter where you look, it should appear roughly the same. Yet when you find a wall over 1 billion light-years long, the assumption of uniformity begins to feel fragile. These discoveries spark ongoing questions about just how smooth the universe really is when you zoom all the way out. Despite their size, these structures remain delicate in a cosmic sense. Over time, dark energy is accelerating the expansion of the universe, stretching space faster and faster. This expansion will eventually loosen the bonds of even the greatest superclusters. Galaxies that are now tied together by gravity may drift apart in the far future, leaving the walls and filaments as faint memories. In the present, however, they stand as monuments to the power of gravity and the web's ability to weave matter into breathtaking forms. When we consider superclusters and walls, we are confronted with the humbling reality of scale. The Milky Way, with its 100 billion stars, is just a single small swirl in Laniakea's vast expanse, and Laniakea itself is just one feature among many, with giants like Shapley tugging on the cosmic stage. Even the Sloan Great Wall, immense as it is, may be only one ridge in a universe full of unseen structures beyond our current reach. The cosmic web stretches far, and every discovery expands our sense of what large really means. There is something poetic about the names we give these structures: immense heaven, great wall, attractor. They capture both the wonder and the mystery of these colossal gatherings. They are reminders that the universe is not only vast but also organized, patterned, and full of connections. The web is not chaos, it is structure, built on scales so immense that human words can only gesture toward their immensity. Superclusters and walls remind us that the universe is a network, a woven structure of unimaginable scale. They are the skyline of the cosmic city, the continents of the universe's map. To know that we live within one of these structures is to feel both small and deeply connected, part of a web that stretches across the heavens. From the Milky Way in its quiet corner of Laniakea to the colossal sweep of the Sloan Great Wall, we're all threads in a structure that reveals the true scope of the cosmos. Every journey needs an address, even a cosmic one. On Earth, your address might include a street, a town, perhaps a country. But if you zoom out far enough, your true location is not on a continent or even on a planet. It is inside a galaxy, inside a cluster, inside a supercluster, all woven into the threads of the cosmic web. To know where the Milky Way sits is to learn our place in this great tapestry. It is our cosmic address. Begin at the smallest scale that feels familiar, the solar system. The Sun, with its family of planets and comets, orbits around the centre of the Milky Way galaxy. Our galaxy is a barred spiral about 100,000 light-years across, home to perhaps 400 billion stars. It is vast beyond comprehension, and yet, compared to the universe at large, it is just a small neighbourhood. The Milky Way belongs to a modest collective of galaxies known as the Local Group. The Local Group contains more than 50 members. The Milky Way and the Andromeda Galaxy are its two giants, with the Triangulum Galaxy as a smaller but still respectable companion. The rest are dwarf galaxies, faint and fragile, circling like little satellites around the larger ones. Most of them are so small they are nearly invisible against the backdrop of the cosmos. Together, the Local Group spans about 10 million light-years. In human terms, that sounds unimaginably large, but in the language of the cosmic web, it is no more than a tiny suburb. The Local Group, in turn, sits on the outskirts of a much larger cluster known as the Virgo cluster. This cluster lies about 55 million light-years away and contains more than 1,000 galaxies. Many of its members are elliptical galaxies, massive and featureless, formed through countless mergers. The Virgo cluster acts as a kind of downtown in our galactic city, the nearest major hub toward which smaller groups like ours are drawn. The Milky Way and Andromeda are like commuters, orbiting within their local suburb but pulled by gravity toward the heart of the Virgo cluster's metropolis. For a long time, astronomers considered the Virgo cluster to be the central defining feature of our larger-scale environment. But in 2014, scientists refined the picture with a discovery that gave us a far more expansive perspective. By mapping the motions of thousands of galaxies, they found that Virgo itself was just part of a far larger supercluster. They named it Laniakea, immense heaven. This became our true cosmic address, a structure about 500 million light-years across, containing over 100,000 galaxies bound in a vast gravitational basin. To define Laniakea, astronomers looked not only at where galaxies are but how they move. Galaxies are not stationary, they drift under the combined tugs of gravity. By tracing these motions, scientists found that our Local Group and the Virgo cluster are all flowing toward a region called the Great Attractor, a mysterious mass concentration that serves as the gravitational centre of Laniakea. This flow is what binds our neighbourhood together, linking us to galaxies hundreds of millions of light-years away. The discovery was like realising that your town is not just part of a nearby city, but part of a vast continent you had never noticed before. Within this continent of galaxies, the Milky Way is one of countless lights along a filament of the web. Our galaxy sits on the edge of the local sheet, a relatively flat arrangement of galaxies that includes Andromeda, Triangulum, and many dwarfs. The local sheet is itself part of a larger structure called the local Supercluster complex, which in turn feeds into the streams of Laniakea. To borrow an earthly metaphor, if the universe is a grand city, the Milky Way is not even a major landmark. It is a modest home on a side street nestled within a sprawling metropolis that extends far beyond our sight. Yet, for us, this modest home feels anything but small. From inside the Milky Way, the night sky glows with hundreds of billions of suns. The band of light we call the Milky Way is the combined radiance of our galaxy's disk, stretching overhead like a river of stars. We orbit within one of its spiral arms, about 27,000 light-years from the galactic centre. It is a safe, relatively quiet neighbourhood, far enough from the dangerous activity at the core but close enough to enjoy the view. In cosmic terms, we live in a stable suburb with a good balance of activity and calm. Placing this home into the context of Laniakea gives us a remarkable sense of scale. Imagine zooming out from the solar system until the Milky Way itself becomes just a dot. Pull back further, and the Local Group becomes a small cluster of dots. Keep zooming, and the Virgo cluster appears, dense with thousands of points of light. Zoom out again, and the filaments of Laniakea come into focus, stretching across 500 million light-years. The Milky Way, once a sprawling spiral in our minds, is reduced to a single glimmer on a single strand of a much larger web. Despite its humbling scale, knowing our cosmic address is strangely comforting. It anchors us in the vastness. We are not lost in a featureless void, we are part of a structured neighbourhood. Our galaxy belongs to a group. Our group belongs to a cluster. Our cluster belongs to a supercluster. And our supercluster belongs to the cosmic web. It is layers upon layers of connection, each one a reminder that even in the enormity of space, we are woven into a pattern. These discoveries also highlight how much more there is to learn. Laniakea may not be the ultimate boundary of our neighbourhood. Beyond it lie other superclusters, other basins of attraction, other immense structures. We do not yet know the full extent of the cosmic web, nor whether the structures we see are the largest possible or just a hint of something grander. Our cosmic address may one day need revising, expanded to include features we have not yet mapped. The universe is a restless architect, and our maps are still works in progress. But for now, Laniakea is home. It is the immense heaven that contains our galaxy, our stars, and our lives. To know that address is to appreciate both the scale of the cosmos and our place within it. The Milky Way is not adrift in chaos. It is part of a vast web connected to galaxies far beyond our reach, all flowing together toward a common centre. When you look up at the night sky, every star you see is a reminder that you are gazing from a small street corner in a very large city. One thread in a web that stretches across the universe. And perhaps the most beautiful part of this cosmic address is the perspective it gives. It reminds us that we belong not only to a planet or a star system, not only to a galaxy, but to an immense heaven of galaxies woven together by gravity. Our true home is not confined to Earth, or even to the Milky Way. It is the web itself, the great lattice of filaments and nodes that holds the universe together. That is our address, written across the stars. The cosmic web, for all its grandeur, is not eternal in its present form. While gravity and dark matter have spent billions of years weaving galaxies into filaments and knots, another force has been working quietly in the opposite direction. This is dark energy, the mysterious agent of expansion that is stretching the web ever further apart. Where gravity gathers, dark energy disperses. The balance between the two has defined the history of the universe, and in the end it may decide the fate of the cosmic web itself. The idea that the universe is expanding is not new. In the 1920s, Edwin Hubble discovered that distant galaxies are racing away from us. Their light stretch to longer, redder wavelengths. The farther a galaxy is, the faster it recedes. At first, astronomers assumed that this expansion was slowing down, as gravity pulled everything back together. After all, it seemed natural that the combined mass of all galaxies, clusters and filaments should gradually tug on one another, slowing the cosmic stretch. It was even debated whether the universe might one day collapse back into a big crunch. That view held until the late 1990s, when two teams of astronomers studied distant supernovae, exploding stars so bright they can be seen across billions of light-years. By using them as standard candles, they could measure how the rate of expansion had changed over time. The results were shocking. Instead of slowing down, the universe's expansion was speeding up. Some unknown force was pushing galaxies apart faster and faster, overpowering gravity on the larger scales. That force was named dark energy, a label that admits our ignorance while acknowledging its undeniable effect. Dark energy is not like anything we experience directly. It does not clump, it does not shine, and it does not dilute as the universe expands. Instead, it seems to be an intrinsic property of space itself. Imagine stretching a rubber sheet. As it grows, you would expect the material to thin out. But in the case of dark energy, the stretching fabric keeps its density constant, as if every new bit of space created comes with a built-in dose of this mysterious pressure. The more the universe expands, the more dark energy there is, and the stronger its effect becomes. For the cosmic web, this has profound consequences. In its early history, gravity had the upper hand. Galaxies streamed along filaments, matter pooled in clusters, and the web became sharper with time. But as the universe aged, dark energy grew more influential. Around 5 billion years ago, its push began to dominate over gravity's pull. From that point onward, the expansion of the universe accelerated, gradually stretching the web's filaments thinner and pulling its nodes further apart. The skeleton of the cosmos is still there, but it is under increasing tension, as though the threads are being tugged at both ends. We can already see the effects. Galaxy clusters that are gravitationally bound will remain together, but those only loosely connected will drift apart. Superclusters like Laniakea may look unified today, but over tens of billions of years, their outer regions will unravel as galaxies accelerate away from one another. The large-scale structure of the universe is frozen in place on smaller scales, where gravity dominates, but stretched apart on larger ones, where dark energy rules. The cosmic web is caught in a tug-of-war, with gravity weaving and dark energy unweaving. The mathematics of this expansion are described by the cosmological constant, a term that Einstein once introduced into his equations of general relativity. He originally added it to keep the universe static, but later called it his greatest blunder when Hubble showed the universe was expanding. Ironically, the discovery of cosmic acceleration resurrected the cosmological constant as the simplest explanation for dark energy. Whether it is truly constant or whether dark energy evolves with time is still an open question, one of the deepest puzzles in physics. To visualize the effect of dark energy on the web, imagine dots connected by elastic bands. Gravity is the elasticity, pulling the dots together. Now imagine slowly inflating the entire frame beneath it. At first, the elastic wins, holding the dots close, but as the frame expands more and more rapidly, the bands stretch, thinning and weakening, until only the tightest knots remain. That is what is happening to the cosmic web. The dense nodes stay bound, while the filaments between them are stretched thin across ever-growing voids. Astronomers test these ideas with surveys of galaxy clustering and with maps of the cosmic microwave background. By comparing the distribution of galaxies today with the ripples frozen in the early universe, they can track how structure has grown under the competing influences of gravity and dark energy. The data show that growth has slowed. Gravity is still pulling matter into filaments and clusters, but the acceleration of expansion is preventing the larger structures from linking up any further. The web is, in a sense, crystallizing. No new great walls or superclusters are likely to form. This raises a haunting vision of the distant future. As dark energy continues its work, galaxies not gravitationally bound to us will slip away beyond our horizon. In trillions of years, observers in the Milky Way may see only their local cluster of galaxies, with the rest of the universe stretched so far apart that its light can no longer reach them. The cosmic web, once a vibrant lattice connecting everything, will appear to vanish, leaving only an island of stars in an otherwise empty dark. For now, though, we're living in a fortunate epoch, when the web is still visible in all its glory. Filaments stretch across hundreds of millions of light years, clusters shine at their intersections, and voids gape between them. Telescopes and surveys allow us to chart this vast architecture, even as dark energy quietly works to pull it apart. It is a cosmic reminder that everything beautiful is also transient, even the largest structures the universe has to offer. And yet there is a certain reassurance in this story. Dark energy does not erase the web instantly. It works slowly, for billions of years, gently reshaping the structure of the cosmos. Gravity and dark matter have done their work, and the filaments they drew will endure for eons before the expansion stretches them beyond recognition. The balance of forces has shifted, but the pattern remains for now, allowing us to see the universe in its most connected and expansive state. dark energy stretch is both a challenge and a gift. It challenges us because it forces us to confront our ignorance. We do not know what it is, why it exists, or whether it will remain constant forever. But it is also a gift, because it allows us to glimpse the cosmic web while it still spans the universe in full. We are living in an age when the structure of the cosmos is still legible, its threads still visible across billions of light years. To look out at the web is to see a universe in tension, a grand architecture drawn by gravity and slowly pulled apart by expansion. In the end, the cosmic web is not just a structure frozen in time, it is a living balance between forces. One that began with the faint ripples of quantum fluctuations was sculpted by dark matter and gravity, and is now being stretched by dark energy. The threads may thin, the nodes may drift, but the memory of the web is written across the sky. Dark energy may win the long game, but gravity has already left its masterpiece, etched into the universe for us to behold. The cosmic web, as we see it today, is a magnificent network of filaments and clusters stretching across the universe. Galaxies ride along its strands, nodes blaze with activity, and voids provide the deep contrast that makes the structure stand out. Yet nothing in the cosmos is permanent. Just as stars are born and eventually burn out, so too will the great web change over time. The question is not whether it will fade, but how and on what timescales. The far future of the universe may look very different from the connected lattice we marvel at today. At the heart of this change lies the tug-of-war between gravity and dark energy. For billions of years, gravity has been the patient builder, gathering matter into filaments and tying galaxies together into knots. But as the universe expands, dark energy has emerged as the dominant influence, accelerating that expansion and stretching the web ever thinner. On small scales, galaxies within clusters remain bound, held tightly by gravity. On larger scales, however, dark energy pulls filaments apart, widening the voids and isolating clusters from one another. Imagine looking at a spiderweb covered in morning dew. At first, the threads glisten, each droplet linked to the others by strands of silk. Now picture the web being pulled at its edges. The threads stretch thinner, some strands snap, and the droplets separate into isolated beads. That is the fate awaiting the cosmic web on timescales of tens of billions of years. The threads of dark matter and galaxies will lengthen and weaken, while the bright nodes at the intersections, galaxy clusters, will become lonely islands in an ever-growing sea of darkness. Already the process has begun. Astronomers observing distant galaxies see them receding faster than nearby ones, carried away by the accelerating expansion of space. Over the next tens of billions of years, this motion will push galaxies further apart until many slip beyond the observable horizon. Their light, stretched to longer and longer wavelengths, will eventually become undetectable. To future observers in our corner of the cosmos, it will appear as though the universe has emptied, leaving only their local cluster visible. The cosmic web will still exist in a larger sense, but it will no longer be seen in its interconnected glory. The timescales involved are staggering. Right now we can observe galaxies more than 13 billion light-years away, and their light still reaches us. But as expansion accelerates, galaxies not bound to us gravitationally will eventually recede faster than light relative to our viewpoint. This does not break physics. It simply means that the expansion of space outpaces light's ability to bridge the gap. Once that happens, their light will never reach us again. The threads connecting us to the rest of the cosmic web will effectively vanish, not because they are gone, but because they have stretched beyond sight. For galaxies within filaments, the future will be a story of dwindling connection. Gas will continue to stream along filaments into clusters, but eventually the supply will thin as the distances grow too large. Without replenishment, star formation will decline. Galaxies will use up their remaining gas, and new generations of stars will become rare. The filaments, once vibrant with the motion of matter, will quieten. They will not snap in a literal sense, but they will fade into near invisibility, stretched so thin that they no longer act as highways of cosmic material. On smaller scales, gravity will still rule. Galaxy clusters like the Virgo cluster and others will hold together as gravitationally bound structures. Within them, galaxies will continue to interact, collide, and merge. Over time, these interactions will give rise to giant elliptical galaxies, vast swarms of stars bound together into smooth, featureless orbs. The lively diversity of spirals, irregulars, and dwarfs will gradually vanish, replaced by these red, aging behemoths. The cosmic web's nodes will survive, but their filaments will become shadows of their former selves. The ultimate picture is one of isolation. Each cluster will become a lone island adrift in an expanding ocean of nothingness. For any civilization living within such a cluster, the night sky will shrink. Galaxies beyond their immediate neighborhood will fade from view, their light stretched beyond detectability. Eventually, they will have no evidence that the cosmic web ever existed. Astronomers of that far future may believe they live in a small, static universe, unaware of the grand network that once connected it all. Only we, and those who live in the present epoch, have the privilege of seeing the web in its full span. Speculation about the distant fate of the universe often goes further still. Trillions of years into the future, stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Galaxy clusters will become dark husks, filled with stellar remnants drifting in near silence. Over unimaginable stretches of time, even those remnants will decay, leaving only the black holes, and in yet deeper epochs, if current theories hold true, even the black holes will evaporate through Hawking radiation. At that stage, the cosmic web will not merely have faded, it will have unravelled completely. Of course, the fate of the web depends on the true nature of dark energy, which remains one of the great mysteries of modern science. If dark energy is constant, the scenario just described is the most likely, a universe that stretches forever, isolating clusters into lonely islands. If dark energy changes with time, the future could be different. Some models suggest it might weaken, allowing gravity to slow expansion again. Others propose a more dramatic fate, the so-called Big Rip, in which dark energy's influence grows without limit, eventually tearing apart galaxies, stars, planets, and even atoms. At present, the evidence points toward a steady, constant dark energy, but the truth remains uncertain. Regardless of the precise outcome, the general picture is one of fading connection. The cosmic web will not last forever in the form we know. Its filaments will stretch, its clusters will grow more isolated, and its once lively exchange of matter will quiet. The grand design we see today is a temporary moment in cosmic history, a phase that will give way to stillness and separation. There is something bittersweet about this vision. The web is the largest structure we know, the greatest architecture ever built, and yet it too is impermanent. And yet, perhaps there is comfort in knowing that impermanence is universal. Stars, galaxies, webs, and even universes change and evolve. Their fading is not an ending but a transformation. The cosmic web will fade, but it will leave behind the memory of its threads, etched into the stars that formed, the planets that spun, and the lives that wondered at them. For now, we live in the golden age of visibility. The web stretches before us, mapped by telescopes and surveys, glowing in our models like the veins of a cosmic leaf. To us, it is real and present. In the deep future, that view will be gone, but the universe will go on, reshaping itself under forces still only partly understood. The web may fade, but for now it is here, binding galaxies across billions of light years and giving us a glimpse of the universe's most majestic design. Long before humanity could map the cosmic web with telescopes, astronomers tried to build it inside computers. If the laws of physics truly govern the universe, then in principle, they can be written as equations fed into a machine and allowed to evolve. Out of that digital experiment, the cosmic web should appear, not as a drawing or a guess, but as a simulation unfolding in virtual time. In practice, this is no small task. The universe is not a tidy system of a few planets orbiting a star. It is billions upon billions of particles interacting across billions of light years. To recreate even a fraction of that requires some of the most powerful computers on Earth. The idea is simple, at least on the surface. Start with the conditions of the early universe, as revealed by the cosmic microwave background. A nearly uniform sea of matter and energy, with faint ripples. Then add the known ingredients: dark matter, dark energy, ordinary matter, and the laws of gravity and physics that dictate how they interact. Give the simulation a starting time. Press the metaphorical button and watch as the universe evolves. Matter begins to clump. Filaments emerge. Clusters form at the nodes, and voids open between them. In a good simulation, the resulting structure should resemble what astronomers observe in reality. One of the pioneering projects in this effort was the Millennium Simulation, launched in 2005. Conducted by the Max Planck Institute for Astrophysics and collaborators, it used 10 billion particles of dark matter to model the evolution of cosmic structure across more than 2 billion light-years of space. At the time, it was the largest calculation of its kind, requiring months of computation on a supercomputer. The result was breathtaking. When the simulation was visualized, it revealed a cosmic web nearly indistinguishable from what surveys like the Sloan Digital Sky Survey had observed. Filaments stretched across the model, nodes glowed with clusters, and vast voids yawned between them. It was as if the universe itself had been reconstructed inside silicon and code. The Millennium Simulation was more than just a pretty picture. It provided a testbed for cosmological theories. By adjusting parameters, the amount of dark matter, the influence of dark energy, the details of how galaxies form within halos, scientists could see how the structure changed. The simulation became a virtual universe where theories could be tested before comparing them to real data. Its predictions guided observations, helping astronomers know what to look for and how to interpret the clustering of galaxies across billions of light years. Building on this, other projects pushed further. The Bolshoi simulation, completed in 2010, focused on smaller scales but with higher resolution. Its name, Russian for great or grand, reflected both its ambition and its success. It modelled the universe with more than 8 billion particles, capturing the intricate details of how dark matter halos, the invisible cocoons around galaxies, formed and evolved. By zooming in on these halos, the Bolshoi simulation provided insights into the distribution of galaxies, the growth of clusters, and the fine structure of the web's filaments. What made Bolshoi especially important was its ability to match observational data with impressive accuracy. The distribution of halos in the simulation agreed closely with what astronomers saw in galaxy surveys. The mass function, essentially the number of halos of a given size, lined up with reality. Even the motions of galaxies, their velocities through space, matched predictions from the model. It was a triumph of computational cosmology, showing that with the right ingredients, supercomputers could indeed recreate the architecture of the universe. These simulations are not mere curiosities. They are crucial tools in modern astronomy. Observations show us the universe as it is, frozen in snapshots of light, arriving after billions of years of travel. Simulations, by contrast, let us watch the universe evolve in fast forward, from the smooth fog of the early cosmos to the richly textured web we see today. They bridge the gap between theory and observation, providing a dynamic story of how structure emerges from simplicity. The technical challenges are immense. Each particle in a simulation represents not a single atom, but a vast clump of dark matter. Tracking their interactions requires solving Newton's laws of gravity for billions of particles at once, a calculation that grows monstrously complex as the numbers increase. Even with supercomputers, compromises must be made. Gas physics, star formation, and feedback from black holes often require simplified models layered onto the dark matter framework. These approximations are constantly refined as simulations become more powerful. Recent projects such as Illustris and Eagle have added even more detail, incorporating the physics of gas cooling, star formation, and feedback from supernovae and active galactic nuclei. These simulations not only reproduce the large-scale web but also generate realistic galaxies within it. The Milky Way and Andromeda appear not as dots of dark matter, but as spirals of stars embedded in halos and connected by filaments of gas. They provide a bridge between the cosmic skeleton and the luminous galaxies we observe directly. There is something deeply satisfying about watching these virtual universes unfold. In animations of the Millennium or Bolshoi results, the screen fills with a glowing lattice, nodes brightening as matter gathers, filaments thickening as streams of material flow along them, and voids expanding as their contents drain away. It is both art and science, a digital symphony of gravity and expansion. The resemblance to the real universe is uncanny, a testament to how well we understand the basic rules governing cosmic evolution. And yet, these simulations also remind us of what we do not know. The nature of dark matter remains elusive, and dark energy is even more mysterious. Simulations can reproduce the web as long as these ingredients are included, but they cannot tell us what they are. They show us how the universe behaves, but not why its deepest components exist in the first place. In this sense, computational cosmology is both a triumph and a humbling reminder of our ignorance. Speculating about the future, it is likely that simulations will only grow more sophisticated. With XZ-scale computing on the horizon, models will be able to include trillions of particles, covering larger volumes with finer resolution. They will trace not only dark matter and galaxies, but also the intricate dance of gas, magnetic fields, and radiation. Perhaps they will even model exotic possibilities, like alternative forms of dark matter, testing which scenarios best match reality. The cosmic web will be recreated in ever sharper detail, until our virtual universes rival the observational ones. For now, the Millennium and Bolshoi simulations stand as landmarks. They showed that with patience, mathematics, and vast computing power, humanity could take the faint ripples of the early universe and watch them blossom into the web of galaxies we see today. They allowed us to hold infinity in the palm of our hands, compressed into code and pixels, and to witness the birth of structure in a universe too large to ever grasp directly. In a way, these simulations are themselves part of the cosmic web. They connect theory with observation, data with imagination, and the human mind with the vast machinery of the cosmos. They remind us that the universe, no matter how infinite it feels, can be recreated, explored, and understood, not only with telescopes gazing outward, but also with computers gazing inward, simulating infinity one calculation at a time. At first glance, the universe and the human brain could not be more different. One is a vast expanse stretching billions of light years across, filled with galaxies, clusters, and filaments of dark matter. The other is a 3-pound organ of flesh and water buzzing with neurons nestled inside a skull. Yet when scientists place maps of the cosmic web beside scans of neural networks, the resemblance is uncanny. Threads of galaxies in the universe and threads of neurons in the brain look strikingly alike, as if nature has chosen to repeat the same pattern at radically different scales. This comparison is not merely a matter of visual coincidence. Both the brain and the cosmic web are networks, systems built not on isolated points, but on connections. In the brain, neurons link to one another through synapses, forming pathways that transmit electrical signals. In the cosmos, galaxies cluster along filaments of dark matter, connected by the pull of gravity. In both cases, the structure is defined less by the individual nodes and more by the way they are tied together. Consider the scale difference for a moment. A neuron is microscopic, measured in fractions of a millimeter. A galaxy is gargantuan, spanning tens of thousands of light years. Yet if you zoom in on a neuron and then zoom out on a galaxy cluster, the branching webs they form could easily be mistaken for the same type of system. The brain contains about 86 billion neurons, while the observable universe holds roughly 2 trillion galaxies. The numbers are different, but both systems rely on enormous networks where complexity arises from connectivity. Scientists have even attempted to quantify this similarity. In 2020, a pair of researchers, one an astrophysicist, the other a neuroscientist, compared the statistical properties of brain networks with those of the cosmic web. They found that despite the difference in scale of nearly 27 orders of magnitude, the two systems shared similar distributions of matter and connections. In other words, the way neurons link to each other in the brain and the way galaxies link through filaments in the universe followed the same mathematical patterns. The cosmos and the brain, it seems, may be distant relatives in the family of networks. Why do such patterns emerge? One answer lies in efficiency. Networks, whether biological or cosmic, evolve towards structures that balance connection with cost. In the brain, neurons form connections that minimize the energy required to send signals while still maintaining robust communication. In the universe, matter flows along paths of least resistance defined by gravity, pooling in nodes and stretching into filaments. Both systems create sprawling webs because webs are an efficient way to connect many points without requiring impossible amounts of material. The comparison invites a certain poetic speculation. If the cosmic web looks like a brain, does that mean the universe itself could be thought of as a kind of mind? Most scientists would caution against taking the analogy too literally. Galaxies do not fire electrical impulses, and voids do not process information in the way neurons do. But the fact that such a comparison arises at all reminds us that nature often prefers repeating motifs. Just as spiral patterns appear in hurricanes, seashells, and galaxies, so too does the web-like architecture of networks appear in both brains and the universe. One might even wonder whether the human brain, as a product of the cosmos, reflects patterns embedded in its origin. After all, we are made of star stuff, as Carl Sagan once said. It is not inconceivable that the same fundamental rules that shape cosmic structure also leave their imprint on the neural structures that give rise to thought. When you think about the universe, you're a network contemplating another network, like a mirror gazing at its reflection. Beyond philosophy, the similarities between the brain and the cosmic web help scientists refine their tools. Techniques developed for studying neural networks, such as methods for analysing connectivity and information flow, can be applied to galaxy surveys. Conversely, statistical techniques from cosmology, used to measure clustering and filamentary structures, can be applied to neuroscience. The resemblance is not only poetic but practical, bridging fields that might otherwise seem unrelated. When you visualize the cosmic web, it is easy to imagine neurons firing. Galaxies cluster like synaptic junctions, filaments stretch like axons, and voids provide the empty space in which signals can travel without interference. In the brain, patterns of firing produce thought, memory, and consciousness. In the universe, the filaments channel gas and dark matter, fueling star formation and galactic growth. Both are systems where connections matter more than their individual points. The scale difference adds a kind of wonder. The brain exists at the scale of centimeters, the universe at the scale of billions of light years. Yet both show that complexity often emerges not from sheer size, but from structure. A single neuron is not conscious, just as a single galaxy is not the web. But connect billions together, and something new arises. Thought in one case, structure in the other. Networks give rise to emergent properties, whether they are the flicker of awareness or the lacework of the cosmos. Some thinkers go further. imagining that consciousness itself might be a kind of network phenomenon that repeats across scales. While such ideas veer into speculation, they reflect a deep intuition that the universe is patterned. The resemblance between brain and cosmos suggests that order does not require design. It can emerge naturally from the simple rules of connection and interaction, applied over and over at different levels. Perhaps the most humbling thought is this: the universe is not just a structure we observe, but the very source of the brain that observes it. The brain contemplating the cosmic web is like a neuron contemplating a galaxy, two ends of a spectrum that mirror one another. The patterns repeat, not because the universe is a brain, but because both obey the same principles of self-organization. The cosmic web is the largest known network, the brain one of the most intricate. Both remind us that complexity arises from connections, not isolation. Whether we are studying neurons firing in millisecond bursts or galaxies flowing along filaments over billions of years, the underlying lesson is the same: nature builds webs, and in those webs, whether of thought or of stars, meaning and beauty emerge. In the end, the comparison between the brain and the universe may be more metaphor than literal truth, but it is a metaphor that speaks deeply to our sense of wonder. To look at the cosmic web is to see the echo of a neural network on the grandest stage. To look at the brain is to glimpse the echo of the cosmos within ourselves. The two are bound not by function but by form, repeating the same graceful geometry across scales so vast that one measures in millimeters and the other in billions of light years. The brain and the universe are different, but in their patterns they share a quiet kinship. Two webs spun by nature, reflecting each other across the gulf of scale. The cosmic web is not only a structure of space, it is a structure of time. When astronomers map its filaments and nodes, they are not simply seeing where galaxies are, they are seeing where galaxies were. Light takes time to travel, and across cosmic distances that time becomes immense. A galaxy 1 billion light-years away appears to us not as it is now, but as it was when the light began its journey, long before humans walked the Earth. A galaxy 10 billion light-years away shows us an even younger version of itself, shining in an epoch when the first great clusters were only beginning to form. To gaze into the cosmic web is to look into a vast time machine, one that holds both history and becoming. Every telescope is, in a sense, an archaeologist of light. The cosmic microwave background shows us the universe as a glowing fog 380,000 years after the Big Bang, a snapshot of its infancy. The nearest galaxies show us the present. Everything in between reveals the stages in between, the slow tightening of filaments, the growth of clusters, the widening of voids. Put together, these observations create a timeline written in threads of matter, each strand stretching not only across space but across billions of years. The web is not static in this story. It is still unfolding, still changing, still shaped by the forces of gravity and expansion. Matter continues to flow along its filaments, gas streaming toward the nodes where galaxies gather and cluster. Observations of distant galaxies, combined with simulations, show that this process is ongoing. Even now, new stars are forming from material delivered by the web. Our own galaxy, the Milky Way, continues to feed on gas streaming in from surrounding filaments, its star formation sustained by these quiet rivers of matter. The cosmic web is not just a relic of the past, it is an active engine of the present. One of the most fascinating aspects of studying the web is how different epochs leave their marks on it. The early universe was smooth, nearly uniform. The faint ripples imprinted in the cosmic microwave background grew into the first filaments. By 1 billion years after the Big Bang, galaxies had begun to form along those filaments, igniting the first stars and black holes. By 5 billion years, clusters had grown at the intersections, voids had deepened, and the web began to resemble the lacework we see today. At 13.5 billion years, its current age, the web is fully developed, though not frozen. Its filaments still draw matter, its clusters still grow and its voids still widen. Looking into deep space is like flipping through an album of cosmic photographs, each one taken at a different time. Galaxies 10 billion light-years away appear small, irregular and young. Galaxies closer to us appear larger, more developed, shaped by billions of years of mergers and star formation. Clusters seen at intermediate distances show us how the nodes of the web grew from modest gatherings into colossal cities of galaxies. Even voids tell a story, expanding over time as matter drains from them into the surrounding filaments. The cosmic web is not just an arrangement, it is a narrative unfolding across the ages. Computer simulations allow us to stitch this narrative together seamlessly, by starting with the conditions of the early universe and letting gravity work. Simulations show how the filaments grew, how gas flowed into halos, how clusters formed at the intersections. They allow us to watch billions of years of cosmic evolution in fast forward, confirming that the web we see today matches the predictions of physics. These models are not only reconstructions but forecasts, showing how the web will continue to stretch under the influence of dark energy, how clusters will become isolated, and how the universe's structure will evolve in epochs yet to come. This dual nature, part history, part living system, makes the cosmic web uniquely captivating. It is at once ancient and new, its filaments holding memories of the earliest quantum fluctuations, while still delivering fresh material for galaxies to grow. Every star in the sky owes its existence to this ongoing process. Even the Sun, with its planets and life, is part of a story that began billions of years earlier, when gas was funneled along a filament into the proto-Milky Way. The thread that nourishes our galaxy is the same thread that carries the memory of the early universe. It is tempting to think of the web as frozen in its present form, a great sculpture etched into space-time. But the truth is more dynamic. The flows along its filaments are like rivers, and rivers are always in motion. Galaxies drift along them, clusters swell at their junctions, and voids hollow out further. Though the pattern may seem unchanging to us, over cosmic timescales it is alive with movement. Just as a tree seems still but grows year by year, so the web grows and shifts over billions of years, each filament a living structure. In some ways, our view of the web is bittersweet. We live at a fortunate moment, when light from distant galaxies still reaches us, allowing us to see the web across its vast span. In the far future, as dark energy stretches space ever faster, much of this light will slip beyond our horizon. The cosmic web will still exist, but it will no longer be visible in its entirety. Future astronomers may see only the local cluster of galaxies, unaware of the grand structure that once stretched around them. Our present view is unique in cosmic history, a window that will eventually close. This adds a poignancy to the study of the web. To map it now is not just an act of science, but an act of preservation, capturing the structure while we still can. Each survey, each simulation, each image of filaments and voids is a record of the web at its most visible moment. Billions of years from now, that record may be the only evidence that such a vast network ever existed. The cosmic web is not eternal in its current form, and yet we are privileged to see it in its prime. Threads of time stretch through every part of the web. They connect the faint ripples of the early universe to the galaxies shining today. They tie the gas still flowing into clusters to the stars that will form in the future. They link the distant past, the present, and the far future in one continuous story of structure and change. To look at the cosmic web is to see not just space, but time itself, woven into the largest fabric imaginable. Perhaps that is the greatest lesson the cosmic web offers. The universe is not a static backdrop, but a living history, a dynamic story unfolding across billions of years. The filaments and nodes we see are both fossils and rivers, recording the past while carrying matter into the future. We, perched on a small planet in the suburbs of the Milky Way, are part of that story. Our own existence is a chapter in the saga of the web, written by threads of time stretching from the beginning of the cosmos to whatever comes after. When you first look at the cosmic web, with its filaments stretching across billions of light years and its clusters burning like beacons, the impression is one of extraordinary order. Galaxies are not scattered haphazardly, but arranged in threads and walls like lacework strung across the void. It feels almost designed, a structure with symmetry and purpose. And yet, peer closer, and you see that this web is also the child of randomness. The filaments began as quantum jitters, fluctuations without pattern or plan. Out of that chaos, gravity and dark matter sculpted structure. The cosmic web is at once chaos and order, entangling both in a pattern that defines the universe. This duality raises an old philosophical question. What do we mean when we call something ordered? The filaments of the web look organized when viewed as a whole, but no single galaxy chose where to be. The threads emerged from countless independent interactions, each particle following simple rules. Just as a flock of birds creates a coordinated pattern without a leader, so too does the cosmic web emerge from the dance of matter under gravity. The order we see is not imposed from above but grown from below, a self-organization that blurs the line between randomness and design. In many ways, the web is an exercise in contrast. Vast voids yawn between filaments, almost empty, while luminous clusters blaze with thousands of galaxies. Without the emptiness, the structure would vanish into uniformity. It is the balance of full and hollow that makes the web visible, just as the pauses between notes make a melody. The cosmic web suggests that order is not simply about filling space with structure, but about how emptiness and fullness interplay. It is a reminder that absence is as important as presence. There is also the question of perspective. From a human viewpoint, the cosmic web seems intricately patterned, perhaps even beautiful. But is beauty really there? Or is it something we project onto the universe? To an ant crawling along one of the filaments, if such a thing were possible, the web would feel endless and chaotic. It is only when viewed from afar that the pattern emerges, the same way a pointillist painting looks like dots up close, but resolves into an image when you step back. In this sense, order and chaos may not be properties of the web itself, but of the scale from which you observe it. Consider the role of randomness in its creation. The original fluctuations in density were quantum in nature, unpredictable and probabilistic. Without those random beginnings, there would be no filaments, no galaxies, no clusters. Chaos, then, was not an obstacle to order, but its seed. Gravity amplified those irregularities into the structures we now see. This is a recurring theme in nature: turbulence creating eddies, randomness shaping evolution, noise giving rise to patterns. The cosmic web is another example of this paradox, where disorder at one level produces harmony at another. Philosophers and scientists alike have long wrestled with whether the universe trends toward chaos or order. Entropy, the great measure of disorder, tells us that the overall tendency is toward randomness. Stars burn out, systems decay, heat spreads. Yet even in this universe ruled by entropy, local structures like galaxies, stars, and planets arise. The web itself is proof that order can emerge within the larger flow of chaos. It may not last forever. Dark energy will eventually stretch it apart, galaxies will burn their fuel, and voids will deepen. But for now, the balance of chaos and order has produced the grandest design we know. There is a poetic irony here. The largest structure in the universe, the cosmic web, was born from the smallest scale of uncertainty: quantum fluctuations. That something so vast could emerge from something so microscopic is a reminder that scale itself is no barrier to pattern. Order and chaos intertwine at every level, from particles to galaxies. The web becomes a mirror of this principle, a demonstration that the line between randomness and structure is not as sharp as we might imagine. It is tempting, gazing at the cosmic web, to ask whether it has meaning beyond its physical existence. Does the pattern suggest purpose, or is it simply the inevitable outcome of physics, beautiful but indifferent? The answer may be both. The web does not exist for our sake, yet it gave rise to the galaxies that formed stars, the stars that forged elements, and the elements that built us. Whether or not it was meant to, the web created the conditions for meaning to arise in beings capable of contemplating it. Its purpose, if it has one, may be nothing more than to make existence possible. The resemblance of the web to other natural forms as neurons, rivers, roots, lightning, suggests that there may be universal rules governing how complexity organizes itself. These rules do not care about scale or substance. They apply equally to stars and to cells. If that is true, then the cosmic web is not unique but part of a deeper pattern, one that shows up whenever matter and energy interact across time. To call this order or chaos is almost beside the point. It is simply nature's way of shaping connections, whether in the soil beneath our feet or in the sky above our heads. One of the most humbling aspects of reflecting on the cosmic web is how fleeting it is in cosmic time. We happen to live in an era when it is visible, when galaxies are still lit with stars and filaments still stretch across the sky. In the distant future, the web will fade, pulled apart by dark energy, until only isolated clusters remain. The order we see will dissolve into apparent emptiness, and yet the memory of the web will persist, imprinted in the galaxies it created, written in the stars that shine today. The interplay of order and chaos will continue, just in different forms. Perhaps the best way to think of the cosmic web is not as one or the other, but as both. It is order grown from chaos, structure balanced by emptiness, permanence fading into impermanence. It shows us that the universe does not need to choose between randomness and design. It embraces both at once. To call the web chaotic is true. To call it ordered is also true. The deeper truth lies in the union, in the recognition that what looks chaotic up close can be ordered from afar, and that what seems ordered now was once chaos waiting to be shaped. When we look at the web, we are really looking at a cosmic paradox. It is the grandest example of order born from disorder, of chaos refined into symmetry. It invites us to accept that the universe is not tidy, but not senseless either. It is both pattern and accident, emptiness and form, and in that paradox lies its greatest beauty. The cosmic web is not a choice between order or chaos. It is the dance of both, woven into the very structure of existence. The universe, when viewed at its larger scales, invites poetry. Astronomers speak in terms of filaments, clusters and voids, but the shapes themselves seem to whisper of lace, fabric and spiderwebs spun across an infinite sky. The cosmic web is not just a scientific structure. It is a tapestry that lends itself to metaphor, a design so vast and delicate that words from both science and art must work together to capture its essence. Imagine lace stretched across darkness. Each thread of the web glows faintly with the light of galaxies, while the holes between them yawn like deep wells of silence. The galaxies are not scattered haphazardly, but arranged as though woven by an unseen hand, each filament connecting to another, each knot marking a gathering of matter where clusters bloom. Like lace on a veil, the cosmic web reveals and conceals at the same time, a pattern etched against emptiness, delicate yet strong, beautiful because of the space it leaves open as much as the strands it reveals. Or think of the web as a fabric, a great cosmic cloth that stretches across the universe. Each filament is a thread, spun from dark matter and stitched with galaxies. Where the threads cross, the weave tightens, forming dense knots, the galaxy clusters that anchor the structure. Where they diverge, the weave loosens, leaving patches of emptiness, the great voids. It is a fabric not made for clothing or shelter, but for existence itself. Without this invisible weave, matter would have remained scattered and diffuse, unable to gather into the stars and planets that form our story. The fabric of the cosmos is not metaphorical. It is literal, a warp and weft of matter and gravity spanning billions of light years. A spiderweb offers another image, perhaps the most evocative. A spider's web is fragile, spun from delicate threads, and yet it can catch and hold. The cosmic web is far vaster, spun not by an arachnid, but by the patient hand of gravity. Galaxies cling to its threads like beads of dew on silk, glittering in the starlight. From a distance, the pattern seems intricate and deliberate, though it arises naturally from simple rules. And like a spiderweb, the cosmic web is both a trap and a lifeline. It captures matter, guiding it along invisible strands, and it sustains galaxies by funneling them the gas they need to grow. It is fragile in its beauty, but resilient in its function. The image of rivers also flows naturally from the web's design. Filaments are not static lines, but channels of motion. Gas and dark matter stream along them, feeding the clusters at their junctions. Galaxies drift as though carried downstream, their fates tied to the currents of the cosmic river. In this vision, the nodes are lakes, reservoirs where material gathers, while the filaments are tributaries connecting them across unimaginable distances. The rivers of the cosmic web carry not water but hydrogen, helium, and dark matter, the lifeblood of the universe. To picture them flowing is to see the cosmos as alive, endlessly circulating its material through channels of gravity. Metaphors multiply because the web is endlessly suggestive. It can be foam, with filaments as the walls and voids as the bubbles. It can be coral, branching and porous, alive with light. It can even be veins, coursing with galaxies instead of blood, giving the impression of a body so large that stars are its cells and clusters its organs. Each image carries its own shade of meaning, reminding us that the universe's largest design resonates with patterns we see everywhere in nature. Lace, fabric, webs, rivers, foam, coral, veins. All are echoes of the same principle, that complexity and connection arise naturally from simple beginnings. There is something deeply calming about these comparisons. They soften the immensity of the universe, giving it forms we can hold in our imagination. Lace can be folded, fabric can be touched, rivers can be followed, spiderwebs admired in morning light. When these images are applied to the cosmos, they make something otherwise incomprehensible feel almost intimate. They remind us that the universe, for all its billions of light years, is not alien but familiar. It is vast, yes, but it is also woven with patterns that repeat across scales, from the veins of a leaf to the filaments of the web. The poetry of structure also reflects a deeper truth about perception. Human beings are pattern seekers. We look at clouds and see shapes, at constellations and see animals, at galaxies and see spirals. The cosmic web in its grandeur invites this instinct to the fullest. We cannot help but see fabric, lace, rivers and webs. Perhaps this is not only a quirk of imagination, but a recognition that nature itself favours such forms. If rivers and veins and spider webs resemble the cosmic web, it may be because all are guided by the same physical principles: flow, connection, efficiency. Even the voids have their poetry. They are not blankness, but breathing space, the negative space that makes the pattern visible. In art, white space is as important as the lines and colours. In music, silence is as important as the notes. In the cosmic web, voids are as important as filaments. They allow the structure to stand out, the clusters to shine brighter, the rivers of galaxies to be traced. The poetry of the web lies not only in what is there, but in what is not. To contemplate these metaphors is to be lulled into a sense of serenity. The universe is not chaos without shape. It is a pattern, delicate yet vast. It is lace embroidered on darkness, fabric woven from invisible strands, rivers flowing between lakes of light. It is a spider web suspended in infinite night, each bead of dew a galaxy, each filament a path for matter to follow. It is both fragile and strong, ephemeral in appearance, but enduring across billions of years. Perhaps the most profound aspect of the cosmic web's poetry is how it connects the human to the cosmic. Lace is human, fabric is human, rivers and webs are part of the natural world we know. By reaching for these images, we bring the universe closer, weaving it into our lives. The web is not distant and abstract, but relatable, its design echoing through the patterns of Earth and the structures of our own making. It is a reminder that the cosmos is not separate from us. We are part of the same lace, the same rivers, the same fabric. The cosmic web is both science and metaphor, data and dream. Its filaments are traced by galaxies, its nodes by clusters, its voids by silence. And yet, when we describe it as lace, fabric, spiderwebs, or rivers, we're not diminishing its reality. We are acknowledging that reality itself invites poetry. The universe is not only measurable, it is also beautiful. Its greatest structure, the cosmic web, is not only a scientific fact but a cosmic poem, written in threads of light and emptiness across the canvas of space. Picture yourself drifting, weightless, through a universe that is both endless and strangely intimate. Around you, space is not empty, but traced with the faintest of lines, invisible to the eye yet holding galaxies like jewels on a string. The cosmic web stretches in every direction, a lattice of gravity and dark matter, its filaments glowing faintly with the collective shimmer of distant stars. You float among them, a quiet traveller carried by currents older than time itself. There is no rush here. The filaments span hundreds of millions of light years, yet they are still, serene, patient. Galaxies cluster in the nodes like lanterns gathered in a faraway festival, their light softened by distance, their bustle hushed by time. In the voids between, silence deepens, so vast it feels like a pause in the breathing of the cosmos. The contrast between fullness and emptiness makes the web what it is, a harmony of presence and absence, threads and gaps, order and quiet. Drifting along these strands, it is easy to think of them as rivers. Streams of matter once flowed here, gas and galaxies pulled by gravity into channels that fed the clusters. Even now, faint currents continue, like water still trickling through old channels long after the flood. If you close your eyes, you can almost feel the pull, a gentle tug guiding you along invisible slopes towards some distant confluence. The journey is not hurried, for the rivers of the cosmos run on timescales far beyond human reckoning. They are patient, eternal flows. The filaments are not lonely roads. They connect galaxies across billions of light years, forming pathways of kinship across the dark. Each galaxy shines with the light of billions of stars, and yet each is only a dot along the thread, one bead among countless others. To see them strung along the filament is to recognize that the universe, though vast, is bound together. No galaxy is truly isolated. Even in the quiet, even in the emptiness, there is connection. As you float deeper into the web, the perspective shifts. The filaments stretch not as straight lines, but as organic forms, branching like the roots of a tree or the veins of a leaf. The voids are bubbles pressed together, like foam on a cosmic sea. The clusters are knots, woven tight with galaxies circling one another in gravitational embrace. The pattern is not rigid but alive, not mechanical but graceful. It feels less like an engineered structure and more like something grown, like lace unfolding on the loom of space-time. It is humbling to rest here, suspended in a structure so vast it dwarfs imagination. The Milky Way, with all its stars and planets and histories, is just one glimmer among billions, woven into a filament that itself is only one of countless threads. And yet, far from feeling small, the sense is one of belonging. The web is not distant from us. We're inside it, part of its fabric, held by the same forces that guide galaxies and clusters. Our own existence is one shimmering strand in this great net of matter and time. The stillness here invites reflection. The web is a record of the past, shaped by ripples born in the first moments of the universe. It is also a work in progress, still flowing, still stretching, still evolving under the hand of gravity and the reach of dark energy. To rest in the threads is to rest between past and future, to pause in a structure that is at once memory and becoming. The galaxies along the filaments shine with histories billions of years old, while their gas flows hint at futures billions of years ahead. Every point is both then and now. There is a paradoxical peace in knowing that such immensity exists. The web does not ask for attention, nor does it demand comprehension. It simply is, unfolding slowly across eons, its beauty hidden until telescopes and simulations revealed it. To imagine yourself here is to release the need for control, to surrender to the scale of things, to drift in the company of galaxies without needing to chart every path. It is rest not in isolation, but in connection so vast it becomes silence. The mind, too, seems to slow in this setting. Just as galaxies are strung on filaments, so thoughts seem to hang on threads of calm, drifting into patterns of their own. The cosmic web becomes a mirror, reminding us that structure arises naturally even in stillness. Just as gravity quietly built the web without hurry, so too can thoughts settle without force, weaving themselves into a gentle fabric of rest. Perhaps this is the poetry of the web's final lesson, that the universe's largest design is also its most tranquil. The filaments are not loud highways, but quiet bridges. The clusters are not noisy cities, but softly glowing gatherings. The voids are not empty wastelands, but spaces that allow the threads to shine. The whole structure is a balance, a harmony of forces, a calm architecture that holds galaxies in its embrace. To float within it is to be cradled by the design of the cosmos itself. Eventually, as you rest in the threads, the immensity becomes familiar, almost intimate. You no longer measure distances in millions of light years, but feel them as gentle intervals, like the spaces between breaths. You no longer think of galaxies as unreachable, but as companions scattered along the same road. The web stops being an object out there in the universe and becomes a space you inhabit, a home vast enough to hold every star and every silence. And so the journey comes to stillness, not with an ending, but with a pause. The cosmic web stretches on endlessly, but here, in the threads, there is peace. You float in the invisible lattice, surrounded by galaxies and voids, by fullness and emptiness, by order and quiet. The universe rests in its own design, and you too can rest within it. The threads of the cosmos cradle you, carrying you into calm, weaving you into the gentle fabric of the infinite night. The cosmic web is one of the universe's grandest revelations, a structure so vast and intricate that it seems to blur the boundary between science and art. It began as a whisper in the early cosmos, faint ripples of density in a nearly uniform fog. Gravity, with patience beyond imagining, drew those ripples into filaments, clusters, and voids. What was once nearly featureless has become an architecture stretching across billions of light years, a pattern that holds galaxies as though they were beads strung along invisible threads. To see it clearly is to see the universe not as chaos, but as a living fabric, woven by the simplest of forces into the most elaborate of designs. And yet the cosmic web is more than just a physical fact. It is a reminder that even emptiness has form. The voids, those immense stretches of near nothing, are not mistakes or afterthoughts. They are the negative spaces that give the structure meaning. Without the voids, the filaments would blur into uniformity. Without silence, there would be no music. The universe's largest design is built not only from galaxies and dark matter, but also from absence, a balance of fullness and nothingness that makes the pattern whole. In the glow of clusters and the darkness of voids, we can read a deeper story about how the cosmos works. Order and chaos are not opposites here, but partners. Random fluctuations gave rise to patterns, and patterns gave rise to galaxies. From the smallest scales of quantum uncertainty to the largest spans of intergalactic filaments, the universe has followed the same quiet principle. Let connections grow, let structure emerge, let simplicity evolve into beauty. The cosmic web is the natural outcome of this principle, a lace of galaxies drawn from randomness, a cathedral of matter raised without plan yet perfectly harmonious. For us, perched in a modest spiral galaxy on the edge of a filament in the supercluster of Laniakea, the web is both a map and a mirror. It tells us where we are, not lost in a sea of stars, but tied into a vast lattice that binds the Milky Way to countless other galaxies. And it tells us something about ourselves, that patterns of connection are universal. The threads of the cosmos echo the threads of the brain, the veins of a leaf, the currents of a river. In every scale of nature the same motifs appear, as if the universe prefers to repeat its most graceful designs. There is comfort in knowing that the larger structure we have discovered is not random but connected. The galaxies we see in the night sky are not drifting aimlessly. They are part of a greater flow, guided by invisible filaments streaming into clusters and forming walls across the void. Even in its silence, the universe speaks of belonging. Every star is tied to a thread, every thread to a node, every node to a web that stretches across the heavens. And we, small as we are woven into it too. The future of the web, like everything in the cosmos, will change. Dark energy is already stretching it thinner, drawing clusters further apart, and in the deep future, much of its beauty will slip beyond visibility. Galaxies not bound to us will fade, their light stretched until it no longer reaches our eyes. The web itself will continue, but from our vantage it will dissolve into isolation. That is why now is a precious time. We live in an era when the cosmic web is visible, when telescopes and surveys can map its threads, when simulations can recreate its growth, and when imagination can find poetry in its form. We are witnesses at the moment of its fullest bloom, and in that bloom lies hope. The cosmic web is a reminder that structure can arise from stillness, that beauty can emerge from chance, and that even emptiness has its role in creating harmony. It teaches us that the universe does not need to be forced into meaning. Meaning is already there, woven into its fabric. When we look at the web, we see not only galaxies, but also the principle that connection itself is fundamental. From atoms to stars, from neurons to filaments, the story is the same. Nothing exists alone. To drift through the web in imagination is to drift through a cathedral of quiet. Filaments stretch like stained glass beams, clusters glow like lanterns, and voids open like vaulted ceilings of shadow. The architecture is both real and dreamlike, scientific and poetic. It is vast enough to humble and gentle enough to soothe. In its presence, anxiety fades, replaced by a sense of being held in something greater, something that has unfolded for billions of years and will continue long after. The cosmic web is, at its heart, a story of patience. Tiny ripples became threads, threads became filaments, filaments became clusters, and out of that slow weaving came galaxies, stars, planets, and life. Our very existence is tied to the web, nourished by its streams, cradled in one of its threads. To rest in that knowledge is to feel the quiet assurance that the universe is not empty chaos but connected structure, not meaningless silence but meaningful pattern. And so, the journey through the web ends not with a conclusion but with a gentle stillness. Picture yourself once more floating in its lattice, weightless among galaxies. Around you stretch threads of light and darkness, each one both ancient and alive. The filaments carry you without hurry, the clusters shine like distant fires, and the voids deepen into serene silence. Here, at the scale of the cosmos, there is no rush, no noise, only the calm architecture of the infinite. The web is both fact and reminder. Fact, because it is the true structure of the universe, mapped and measured. Reminder, because it shows us that connection and beauty can arise even out of emptiness. To know it is to glimpse both the science of the cosmos and the poetry of existence. And as you rest within its threads, you may find yourself not overwhelmed but comforted. For in the largest design ever revealed, you are already woven in. Drifting through the cosmic web is drifting through quiet belonging. Its threads stretch endlessly, but within them there is peace. The universe is vast, yes, but it is also connected, patient, and calm. Even emptiness has form, and even silence has meaning. The story of the web is still unfolding, but tonight you are free to rest in its threads, cradled by the gentle architecture of the universe.